Picture this: you're floating in the deepest, darkest void of space, surrounded by a sea of silent stars, and then you see it, a colossal island of light, a galaxy so enormous it defies comprehension. This is NGC 4889, a supergiant elliptical galaxy anchored in the heart of the Coma Cluster, over 300 million light-years from Earth. It's a place where the known laws of physics seem to bend, twist, and sometimes completely unravel. What secrets lie within this cosmic giant, and why do some of its most stunning features remain unexplained even to the most brilliant scientific minds? Galaxies are often described as the cities of the universe, but NGC 4889 is more like a forgotten metropolis where reality itself feels distorted. Here, black holes of unimaginable scale lurk in its core, gravitational waves warp the paths of light, and mysterious energy emissions flicker like signals from another dimension. Every observation raises more questions than answers. Why are stars moving in ways that shouldn't be possible? What is the source of those strange radiation bursts that telescopes pick up but cannot decode? Step by step, we're going to explore 30 of the most peculiar and awe-inspiring phenomena tied to this galaxy phenomena that challenge everything we think we know about the cosmos. This journey isn't just about listing facts or sharing stunning visuals. It's an invitation to wonder, to reconnect with that childlike curiosity about what lies beyond our world. Whether you're an avid space enthusiast or someone who simply gazes up at the night sky with a sense of awe, there's something deeply human about confronting the unknown. And that's exactly what we're about to do together. From unexplained dark matter interactions to energetic anomalies that have left astronomers speechless, we're setting off on a voyage into one of the universe's most captivating mysteries. So settle in, open your mind, and get ready, because what we're about to uncover may just change how you see the cosmos forever. Our journey into the unknown begins at the very heart of the galaxy, with a behemoth so vast it once held the title of the largest black hole ever discovered. Tipping the scales at an estimated 21 billion times the mass of our Sun, the supermassive black hole at the core of NGC 4889 is a true monster of the cosmos. To put that incomprehensible scale into perspective, our own Milky Way's central black hole, Sagittarius, a star, is a mere 4 million solar masses. This galactic giant is thousands of times larger. You would expect such an object to be a frenetic engine of destruction, a blindingly bright quasar tearing through the fabric of space with an insatiable appetite. And yet, when we point our most powerful telescopes toward it, we are met with a profound and puzzling silence. This colossus appears to be in a deep slumber, a dormant phantom that offers few of the energetic outbursts typically associated with black holes of its stature. This state of quietude challenges some of our fundamental ideas about how these cosmic giants live and die. A supermassive black hole is typically an active, violent place. As it pulls in gas, dust, and even stars, this material doesn't just vanish quietly. It forms a superheated accretion disk, a swirling whirlpool of matter that spirals inward at nearly the speed of light, releasing tremendous amounts of energy as X-rays and gamma rays before crossing the event horizon. The fact that we detect so little of this activity around such a massive object is what makes this a genuine cosmic mystery. It raises a compelling question. Has this black hole simply consumed all the available fuel in its immediate vicinity, leaving it in a temporary state of hibernation? Or are we witnessing a new, later stage in the life cycle of a supermassive black hole that our models have not yet predicted? One leading theory suggests that the very nature of its home, an old elliptical galaxy, provides a clue. Unlike spiral galaxies, which are rich with the gas and dust needed to form new stars and feed a hungry black hole, elliptical galaxies like NGC 4889 are often considered cosmic retirement communities. They are filled with older, redder stars and contain far less interstellar material. It's possible the black hole has effectively cleaned its plate, having gone through a spectacularly violent active phase in the distant past that ejected or consumed all nearby matter, forcing it into a period of quiet retirement. This would have been an era of unimaginable power, a quasar outburst so intense it could have shaped the evolution of the entire galaxy around it. Now we see only the aftermath, a sleeping giant surrounded by the evidence of its past feasts. This phantom at the galaxy's core forces astronomers to reconsider the timeline of black hole activity. Its dormancy suggests that even the most massive objects in the universe may have active and inactive phases that last for millions or even billions of years. We might simply be observing it during a cosmic pause, a chapter of calm in a long and violent biography. Studying this silent leviathan helps us piece together the life story of supermassive black holes, hinting that their most explosive and energetic periods are not their entire identity, but merely a single dramatic chapter. But the enigma of this silent giant is only the beginning. As we pull our view back from the central black hole to examine the wider galaxy, we encounter a second, perhaps even more profound mystery that challenges our understanding of the universe's very scaffolding. For a galaxy of its immense size and mass, nestled within the crowded Coma Cluster, NGC 4889 should be enveloped in an enormous, massive halo of dark matter. This invisible, mysterious substance is the gravitational glue that holds galaxies together and governs their formation and rotation. And yet, when astronomers measured the gravitational forces at play within this supergiant elliptical, they were met with a startling and counterintuitive discovery. The dark matter halo they expected to find appears to be missing. This finding is so peculiar because it defies a fundamental rule of modern cosmology. We observe that all galaxies, from small dwarfs to large spirals like our Milky Way, are embedded within these vast spheres of dark matter which can extend far beyond the visible starlight. These halos are not just incidental, they are essential. Without the immense gravitational pull of dark matter, a galaxy would simply fly apart as it spins. The visible stars alone do not provide enough gravity to hold everything together. For a galaxy as enormous as NGC 4889, which boasts a stellar mass of hundreds of billions of suns, the dark matter halo should be correspondingly colossal, a truly titanic structure anchoring it in space. The fact that it seems to be absent, or at least significantly diminished, forces us to ask a deeply unsettling question. Have we misunderstood how dark matter operates in the most extreme environments in the universe? So how did astronomers even detect something that is, by its very nature, invisible? They use clever methods of observation and deduction. By carefully studying the motion of stars within the galaxy and the movement of smaller satellite galaxies and globular clusters orbiting around it, scientists can map out the total gravitational field. This tells them how much mass is present and where it is concentrated. What they found was that the visible mass of stars, gas, and the central black hole almost entirely accounts for the gravity they measure. There is little to no evidence of the extra, unseen mass that a dark matter halo should be providing. It's as if you weighed a closed box and found it was exactly as heavy as the known objects inside, with no hidden weight adding to the total. One compelling theory to explain this anomaly points to the violent, dense environment of the Coma Cluster itself. Galaxy clusters are the most massive gravitationally bound structures in the cosmos, and they are bustling cities of galaxies constantly interacting, merging, and stripping material from one another. It's possible that through billions of years of chaotic gravitational encounters with neighboring galaxies, NGC 4889 had its dark matter halo effectively torn away and stripped from it. In this scenario, the visible stars, which are densely packed in the galaxy's core, would have held together due to their own gravity, while the more diffuse dark matter spread out in a vast halo, was pulled away and absorbed into the general dark matter background of the entire cluster. We'd be looking at a galaxy that has been robbed of its dark mantle, leaving its bright stellar body exposed. This possibility opens up a new window into the dynamic life cycle of dark matter. It suggests that dark matter is not permanently and inflexibly bound to a single galaxy, but can be redistributed on a colossal scale through cosmic interactions. If true, it means the distribution of dark matter in the universe is far more fluid and complex than our current models often assume. The missing halo of NGC 4889 isn't just a curious oddity. It's a potential clue, a piece of evidence that could help us finally understand the properties of dark matter itself, how it interacts with itself and with gravity under the most extreme conditions. This galactic phantom is challenging us to look deeper, pushing the boundaries of what we know about the invisible framework of the cosmos. Perhaps most visually stunning among the galaxy's mysteries is a celestial magic trick gone slightly wrong, a phenomenon where the fabric of space itself behaves in ways we cannot fully explain. As predicted by Einstein's theory of general relativity, the immense gravitational field of a massive object like NGC 4889 should act as a lens, bending and magnifying the light from even more distant galaxies lying behind it. This effect, known as gravitational lensing, is a powerful tool astronomers use to map the distribution of mass, both seen and unseen. Around this supergiant galaxy, the lensing effects are certainly dramatic, creating spectacular arcs and multiple mirage-like images of background objects. But when scientists compare these observed distortions to the sophisticated models predicting what the lensing should look like, based on the visible stars and the presumed dark matter, the two maps do not align. The real universe is creating patterns the models never anticipated. These anomalies manifest in several puzzling ways. In some cases, astronomers detect unexpected multiple images of a single background quasar, arranged in patterns that shouldn't be possible given the understood mass distribution. It's as if the galaxy contains invisible lenses within the main lens, subtly altering the light's path in a complex way that our simulations can't replicate. In other areas, the warping of background galaxies appears either too strong or too weak, suggesting concentrations of mass that are either missing or present where our models say there should be nothing. These gravitational lensing discrepancies are not just minor calculation errors. They are significant enough to point toward a gap in our understanding of how mass is structured in such an immense system, or perhaps even a subtle flaw in our comprehension of gravity itself on the largest scales. One compelling hypothesis to explain these warping patterns proposes the existence of a population of dark matter substructures, or subhalos, orbiting within the main galaxy. Think of it like looking through a lumpy pane of glass at a distant street lamp. The imperfections in the glass create additional distortions and multiple blurry images of the single light. In this cosmic analogy, the lumpiness would be caused by clumps of dark matter, smaller than the main halo but still incredibly massive, drifting through the outskirts of NGC 4889. Their concentrated gravity would then act as secondary lenses, adding their own unique fingerprint to the overall warping effect. The problem is, our current cosmological simulations predict a certain number and size of these subhalos, and the lensing anomalies observed here seem to require either more of them or ones of a different mass than the models allow. This leads to another, more radical possibility, that we are seeing hints of something beyond the standard model of particle physics for dark matter. Most models assume dark matter is cold and collisionless, meaning its particles move relatively slowly and mostly pass through each other and normal matter without interacting. But what if dark matter has just a tiny bit of interaction, enough for it to clump and structure itself in ways we haven't predicted? The strange lensing patterns could be the first observational evidence for such self-interacting dark matter, a property that would fundamentally reshape our search for this elusive substance. Alternatively, the anomalies could be pointing toward a need to modify our theory of gravity itself, though this remains a more contentious proposal within the scientific community. Each distorted image and unexpected warp is therefore more than just a pretty picture. It is a data point in a high-stakes cosmic experiment. By meticulously reverse engineering these gravitational lensing anomalies, astronomers are using NGC 4889 as a natural laboratory to stress test the very foundations of modern cosmology. The galaxy's immense gravity provides the lens, and its puzzling output is challenging us to see the universe and its hidden components more clearly than ever before. Moving from the warped light of gravitational lensing, we arrive at another profound silence echoing from this cosmic giant. Despite its staggering size and a history that almost certainly included a ferociously active phase, NGC 4889 emits a puzzlingly faint whisper in the radio part of the electromagnetic spectrum. This radio silence is a true enigma because it directly contradicts what we observe in other galaxies of its type. Most massive elliptical galaxies are prolific producers of radio waves, often broadcasting powerful signals generated by jets of superheated particles shooting out from their central black holes at near light speed. These radio lobes can span millions of light years, acting as lasting monuments to the violent activity within. Yet, when we train our radio telescopes on NGC 4889, we are met with a profound and unexpected quiet. This absence of loud radio noise tells a complex story about the galaxy's current condition. Those powerful radio emissions typically come from a very specific process. When a supermassive black hole is actively feeding, not all the material in its accretion disk gets swallowed. Intense magnetic fields can funnel some of the inflowing gas and dust into focused beams or jets that erupt from the black hole's poles and blast far out into intergalactic space. These jets, packed with energetic particles, interact with the tenuous gas between galaxies to create colossal, bubble-like structures that glow brightly at radio frequencies. The fact that we don't see these structures around NGC 4889 is the strongest evidence that its central engine has truly shut down. The jets have switched off, and without that ongoing energy injection, any ancient radio bubbles from its active past have long since faded away, dissipated into the quiet of the cluster. This leads to a fascinating question of timing. The radio silence suggests we are witnessing this galaxy at a very specific and perhaps very late stage in its life cycle. It has likely already progressed through its most tumultuous chapters. The radio-loud phase for a galaxy like this might last for tens or even hundreds of millions of years, but that is still just a fraction of its multi-billion-year existence. We may be seeing it during an extended period of peace, a cosmic retirement that follows an incredibly energetic youth. It's possible that the black hole's past outbursts were so powerful that they effectively cleared out the entire central region of fuel, starving itself and forcing it into a dormant state from which it cannot easily wake. Another layer to this mystery involves the environment itself. NGC 4889 resides in the densely populated Coma Cluster, a region filled with a superheated plasma known as the intracluster medium. This thin but incredibly hot gas suffuses the space between galaxies in the cluster. For a galaxy moving through this medium, there is a constant pressure, a kind of cosmic headwind, that can physically strip away the cooler gas reservoirs that might otherwise fall inward and reignite the black hole. This process, called ram pressure stripping, could be acting as a maintenance crew, constantly cleaning up any potential fuel before it has a chance to reach the center and turn the lights back on. The galaxy's radio silence, therefore, might not just be about its internal state, but also a consequence of its busy galactic neighborhood preventing it from getting a fresh meal. This unusual quiet makes NGC 4889 a crucial control subject for astronomers. By studying it alongside its radio-loud cousins, scientists can better understand the triggers that turn a black hole's activity on and off. Its silence is not an absence of information but a valuable data point in itself, telling us about the final stages of galactic evolution and the environmental factors that can lead to the permanent quieting of a cosmic giant. It shows us that even the most powerful engines in the universe eventually run out of fuel, leaving behind a silent monument to their past ferocity. Yet another layer to this paradox is found in the galaxy's vast outer halo. Here, astronomers have identified streams of stars and faint, delicate structures that look like the dissolving remnants of smaller galaxies that were torn apart and absorbed by NGC 4889's immense gravity. This process, known as galactic cannibalism, is common in dense clusters, and it provides a potential delivery mechanism for fresh star-forming fuel. A captured dwarf galaxy might bring with it reservoirs of unspent cold gas. As this foreign gas is compressed during the merger process, it could ignite a final, brief burst of star formation, sprinkling young blue stars across the older population like a handful of diamonds thrown onto a bed of gold. These stellar immigrants would then tell a very different story about their birth than the native stars around them, creating a mixed and confusing timeline for observers millions of light years away. The implications of this stellar age paradox reach far beyond this single galaxy. It challenges the classic view of elliptical galaxies as simple, red and dead systems whose evolutionary stories concluded long ago. Instead, NGC 4889 appears to be a dynamic and complex entity, capable of experiencing delayed or rejuvenated chapters of star birth through a combination of internal recycling and external acquisition. This forces astronomers to reconsider the life cycle of the universe's largest galaxies, suggesting that their evolution is not a linear path to quiet retirement, but a more nuanced narrative with potential for late-stage activity. The presence of these surprisingly young stars is a powerful testament to the fact that even in the oldest and most seemingly quiescent neighborhoods of the universe, the forces of creation can still find a way. Deep within the seething hot atmosphere of the Coma Cluster surrounding the galaxy itself, astronomers have mapped a pair of truly colossal voids. These are not mere empty spaces, but perfectly spherical cavities carved out of the multimillion-degree plasma that envelops NGC 4889. This superheated gas should glow with intense X-rays, yet these vast bubbles are strangely dim, appearing as near-perfect spheres of silence within the energetic haze. Their existence and their incredible symmetry presents a classic cosmic whodunit, pointing to a violent release of energy in the galaxy's past that was powerful enough to sculpt the very intergalactic medium and leave behind ghostly imprints that have lasted for hundreds of millions of years. The leading theory for their creation points directly to the now dormant supermassive black hole at the galaxy's heart. Astronomers believe these cavities are the fossilized remnants of two gigantic jets that once erupted from the black hole during its active quasar phase. As these jets, moving at nearly the speed of light, plowed outwards into the surrounding cluster gas, they acted like cosmic plowshares, pushing the hot plasma aside and creating these immense bubble-like structures. The reason they appear as cavities in X-ray observations is simple. The jets have shoved the dense, X-ray bright gas out of the way, leaving behind a much more diffuse and faint region. They are essentially the lasting scars of a titanic outburst, a permanent record of the black hole's past fury written in the negative space of the intracluster medium. What makes these bubbles a genuine puzzle, however, is not just their existence, but their pristine, spherical shape and remarkable longevity. According to basic physics, such enormous low-density voids in a high-pressure environment should not last. The intense pressure from the surrounding hot gas should have caused these bubbles to collapse, distort, or dissipate long ago. The fact that they haven't, that they maintain their perfect forms against the relentless forces that seek to erase them, suggests they are being supported or inflated by something from within. It's akin to blowing a bubble in a thick syrup and watching it hold its perfect round shape for years instead of seconds. One compelling explanation is that the bubbles are not truly empty. They are filled with something else, a very thin but incredibly hot and magnetized plasma that was injected by the original black hole jets. This internal gas, while tenuous, might be so energized that it exerts its own outward pressure, acting like a durable balloon that fights against the inward crush of the external cluster gas. Furthermore, magnetic fields woven through the material by the jets themselves could be providing a supporting structure, a rigid cage that helps the bubble maintain its spherical integrity far longer than simple gas pressure alone would allow. This combination of internal energy and magnetic scaffolding could be the secret to their cosmic longevity. Studying these X-ray cavities gives astronomers a unique way to perform an archaeological dig into the galaxy's most violent era. By measuring the size of the bubbles and the properties of the surrounding gas, scientists can essentially work backwards to calculate the immense amount of energy required to create them. The numbers are staggering, suggesting the black hole's outburst released energy equivalent to the simultaneous explosion of billions of supernovae. This single event would have been a defining moment for the entire galaxy, likely shutting down star formation by violently heating and expelling any remaining cool gas and forever altering its evolutionary path. These silent, spherical voids are therefore more than just curiosities. They are the key to understanding the most catastrophic and transformative event in the history of NGC 4889. Surrounding this galactic titan, the mysteries only deepen with the discovery of a ghostly entourage. Orbiting NGC 4889 are numerous ultra-diffuse galaxies, or UDGS, faint and wispy collections of stars that are as large as the Milky Way but contain only a tiny fraction of its stars. These are the ghosts of the cosmos, and they appear to be moving in strangely synchronized patterns, as if choreographed by the immense gravity of the central supergiant. This gravitational relationship is far more complex and puzzling than it first appears, offering a unique window into the subtle and invisible forces that govern the largest structures in the universe. The sheer number of these ultra-diffuse galaxies in the vicinity of NGC 4889 is the first clue that something unusual is happening. Galaxy clusters are crowded places, but the concentration of UDGS around this particular giant seems unusually high. What's truly remarkable, however, is not just their presence but their behavior. Through painstaking observations, astronomers have mapped their motions and found that many are not moving randomly. Instead, they appear to be tracing out ordered orbits, almost like planets moving around a star, but on a scale that is almost impossible to comprehend. This level of organization is startling because the chaotic gravitational tug of war within a dense cluster should make such precise orbital patterns nearly impossible to maintain over long periods of time. This is where the dark matter puzzle resurfaces in a fascinating new form. The leading theory for why these ultra-diffuse galaxies are so diffuse, so spread out and lacking in stars is that they are incredibly rich in dark matter. It's thought that their dark matter halos are exceptionally massive and dominant, providing the gravitational pull that holds their sparse stars together despite their wide distribution. Their apparent orchestrated dance around NGC 4889, therefore, isn't just a dance between visible objects. It's primarily a complex interaction between their immense dark matter halos and the gravitational field of the central galaxy. We are essentially witnessing a shadow ballet where the visible stars are just tracers following the lead of their invisible dark matter components. This gravitational interplay provides astronomers with a rare and valuable natural experiment. By carefully tracking the precise movements of these ultra-diffuse galaxies, scientists can create a detailed map of the gravitational landscape surrounding NGC 4889. This map, in turn, reveals the total distribution of mass both visible and dark in 3 dimensions. The ordered orbits of the UDGS suggest that the gravitational field is smoother and more organized than our models predicted for such a chaotic environment. This could be indirect evidence that the missing dark matter halo of the central galaxy is not entirely gone, but has instead been stretched and smoothed into a vast, faint web that extends far beyond its visible stars, a web whose subtle tides are gently guiding these ghostly satellites. Another compelling possibility is that these ultra-diffuse galaxies are not independent actors at all, but the surviving cores of much larger galaxies that were torn apart by NGC 4889's gravitational pull billions of years ago. In this scenario, a smaller galaxy would have its outer stars and dark matter stripped away during a close encounter, leaving behind only its dense, dark matter-rich core to continue orbiting. This process could naturally explain why the remaining UDGS are so dark matter-dominated, and why their orbits might retain a memory of that initial traumatic interaction. They would be the cosmic equivalents of survivors, forever bound to the giant that shaped their destiny. Studying this relationship is pushing the limits of our observational technology. These galaxies are extremely faint, and mapping their precise motions requires countless hours on the world's most powerful telescopes. Each new data point adds another piece to the puzzle, helping us understand not only the history of this specific cluster, but also the fundamental nature of dark matter itself. The way these dark matter-rich satellites respond to gravity could reveal subtle properties of dark matter particles, such as whether they can interact with each other in ways beyond simple gravity. The silent, precise dance of the ghosts around the giant is more than a celestial curiosity. It is a delicate experiment playing out on a galactic scale, offering clues to the invisible architecture of the universe. Now we arrive at a phenomenon that seems to bend the very fabric of time itself. When astronomers study the cataclysmic deaths of stars, they rely on a predictable clock, the light curve of a supernova. For a specific type of stellar explosion known as a Type 1, a supernova, this brightening and fading follows an incredibly consistent and well-understood pattern. It's one of the most reliable cosmic yardsticks we have, but for a handful of these supernovae that have been observed on the far side of NGC 4889, that reliable clock appears to have been subtly manipulated. The light we receive from these explosions seems to have experienced a different flow of time than our models of gravity predict, a discrepancy that points toward forces at work we do not yet fully comprehend. This effect is rooted in one of the most fascinating consequences of Einstein's theory of general relativity, gravitational time dilation. The theory states that the stronger the gravitational field, the slower time itself will pass from the perspective of a distant observer. We know this is real. It's a measurable effect here in our own solar system, and our GPS satellites must account for it to provide accurate positioning. In the context of a supergiant galaxy, the light from a background supernova must climb out of the immense gravitational well of NGC 4889 to reach our telescopes. This journey should cause a very specific and calculable delay, stretching out the supernova's light curve in a predictable way. The mystery is that for some of these events, the observed stretching is either too much or too little. The light curve is either too smoothed out, as if time passed even slower for that light than it should have, or not smoothed out enough, suggesting a weaker gravitational pull than expected. The implications of these tiny temporal anomalies are profound. If the time dilation is greater than predicted, it implies the gravitational pull of the galaxy is stronger than the sum of its visible parts should allow for. This could be the signature of a hidden concentration of mass, perhaps a vast and previously undetected clump of dark matter warping space-time more severely in that particular path. Alternatively, if the time dilation is weaker than expected, it suggests a gravitational field that is somehow less potent, adding another layer of intrigue to the puzzle of the galaxy's seemingly missing dark matter halo. In either case, these supernovae are acting as precise probes, their light curves serving as highly sensitive instruments that measure the true gravitational landscape along their specific line of sight. One of the most compelling explanations for these discrepancies involves the potential presence of what physicists call exotic matter. This isn't just dark matter, but matter with truly strange properties, such as negative mass or negative energy. While this sounds like science fiction, certain theoretical fields in quantum physics and cosmology allow for its existence. If such exotic matter were concentrated in certain regions around the galaxy, its bizarre gravitational influence could either enhance or diminish the time dilation effect in ways that normal matter simply cannot, creating the observed mismatches in the supernova data. We would be witnessing the indirect fingerprints of a substance that fundamentally alters the rules of space and time. Another possibility is that our understanding of gravity itself requires refinement in these most extreme environments. The equations of general relativity have passed every test thrown at them for over a century, but they have never been rigorously tested in a gravitational field as immense and complex as that of a supergiant galaxy embedded in a dense cluster. It is conceivable that under these conditions, gravity behaves in a subtly different way, a deviation that would only reveal itself through ultra-precise measurements like these time-delayed light curves. Each anomalous supernova is therefore a potential arrow pointing toward a deeper, more complete theory of the universe. What makes this particular mystery so captivating is that it uses the most violent and energetic events in the universe as a tool to measure one of the most subtle and fundamental forces. We are leveraging the death throes of stars to act as cosmic stopwatches, and their errant ticking is telling us that near NGC 4889, the flow of time itself may not be what we think it is. It is a testament to how the cosmos constantly provides new experiments, challenging us to listen more carefully and interpret more wisely the ancient light that has traveled so far to bring us its message. Now we descend from the scale of galaxies and stars to the realm of the impossibly small, where the very definition of nothing becomes a source of profound mystery. The space surrounding NGC 4889 is not truly empty. Even in the deepest voids between stars, space itself is alive with a faint, seething energy. According to quantum mechanics, the vacuum is a bubbling sea of virtual particles, pairs of particles and antiparticles that constantly flicker into and out of existence for unimaginably short instants. This activity, known as quantum vacuum fluctuation, is a well-established part of modern physics. But here, in the extreme gravitational shadow of this supergiant galaxy, the vacuum itself appears to be behaving strangely. Astronomers have detected faint, anomalous energy signatures that suggest these quantum fluctuations are far more energetic, or perhaps structured in a more complex way than our best theories predict. These anomalies manifest as subtle excesses of energy in certain wavelengths of light, or as tiny, unexplained variations in the polarization of background radiation passing through the galaxy's outskirts. It's as if the vacuum around NGC 4889 is somehow more active, more potent than the empty space elsewhere in the universe. This is deeply puzzling because the rules of quantum field theory are supposed to be universal, the same everywhere. The vacuum should be the vacuum. The fact that it seems to be different in this specific location suggests that something about this extreme environment is modifying the fundamental behavior of space-time itself, a discovery that could force a major rewrite of our understanding of quantum physics. One of the most compelling hypotheses for this strange vacuum activity involves the galaxy's titanic gravitational field. Einstein taught us that gravity is the curvature of space-time by mass. The supermassive black hole and the immense concentration of stars in NGC 4889 create one of the most severely warped regions of space-time in the known universe. Some theoretical physicists propose that this extreme curvature could be amplifying the quantum fluctuations, effectively stirring the vacuum and drawing more energy out of it. It's analogous to how a strong wind can whip a calm sea into a turbulent froth. The gravitational wind of the galaxy might be agitating the quantum sea of virtual particles to a far greater degree than we've ever observed before. This leads to an even more radical possibility that we are seeing indirect evidence for a connection between gravity and quantum mechanics, a link that has eluded physicists for a century. Our two most successful theories, general relativity for the cosmic scale and quantum mechanics for the subatomic scale, are famously incompatible. The vacuum around this galaxy could be a unique natural laboratory where these two fundamental forces meet and interact in a way we can actually observe. The anomalous energy patterns might be the signature of quantum gravity effects, a glimpse of the physics that will eventually succeed and unify both theories. We could be witnessing the vacuum itself responding to gravity in a way that our current quantum equations simply don't account for. Another fascinating theory suggests the culprit might be an unknown field permeating the cosmos. Much like the Higgs field gives particles their mass, there could be other, undiscovered fields that interact with the vacuum. The immense mass of NGC 4889 might be acting as a lens, concentrating the influence of this hypothetical field in its vicinity and making its effects on the quantum vacuum detectable for the first time. This would not only explain the strange energy patterns, but could also provide a major clue in the search for physics beyond the standard model, potentially offering insights into the nature of dark energy or the origins of the universe itself. Investigating this phenomenon is a monumental technical challenge. Detecting the faint whisper of quantum vacuum fluctuations across hundreds of millions of light years requires exquisitely sensitive instruments and painstaking analysis to rule out all other possible sources of interference. Each new observation is a step into the unknown, probing the most fundamental layer of reality in an environment where the rules seem to be subtly different. The strange quantum vacuum around NGC 4889 reminds us that even nothing is something, and that in the most extreme corners of the cosmos, the very fabric of reality can reveal new secrets that challenge our deepest understandings. Even in its apparent state of dormancy, the heart of this galactic giant is not entirely still. Astronomers have detected a faint but persistent heartbeat, a series of low-frequency, rhythmic pulsations emanating from the very core of NGC 4889. This galactic core oscillation is one of its most baffling mysteries because it originates from a region that, by all accounts, should be silent. The supermassive black hole is sleeping, and yet something is causing the very fabric of space around it to thrum with a regular, predictable cadence, a pulse that can be detected as subtle variations in X-ray and radio emissions repeating over a timescale of many months. Detecting this faint rhythm is a triumph of modern astrophysics. It requires combining data over long periods from multiple space-based observatories tuned to different wavelengths. In X-rays, scientists observe a tiny, periodic brightening and dimming of the hot gas that still lingers far from the event horizon. In radio waves, there is a corresponding, almost imperceptible flicker. By themselves, these individual signals might be dismissed as random noise or instrumental error, but their synchronization across the electromagnetic spectrum and their unwavering regularity point to a genuine, coordinated phenomenon happening deep within the galaxy's gravitational well. It is the equivalent of placing a stethoscope on the chest of a sleeping giant and hearing a slow, steady heartbeat. The existence of this pulse immediately challenges the notion of a completely dormant black hole. It suggests that while the engine may be off, the pilot light is still flickering. The leading explanation proposes a slow, grinding feast is still underway. Even in its retired state, the black hole's gravity is immense, and a trickle of material, perhaps in the form of stray gas clouds or the shredded remnants of small stars, must still be drifting inward. This material doesn't fall in a smooth stream, but in clumps and irregular pieces. As each clump spirals closer on its final journey, it interacts with the treacherous environment around the black hole, releasing bursts of energy that we detect as individual pulses in the overall rhythm. However, the exquisite regularity of the oscillation is difficult to explain with random, infalling debris alone. That clock-like precision has led to another, more exotic theory. The pulse may be caused by a persistent, stable structure within the accretion flow itself. Imagine a vast, donut-shaped ring of gas and dust that survived the black hole's active phase, trapped in a stable orbit just beyond the point of no return. This ring, or torus, could be wobbling like a slow-motion gyroscope under the influence of the black hole's spin and the gravitational pull of the surrounding stars. Each full wobble would periodically bring part of the ring closer to the hungry void, triggering a small release of energy that we see as a single pulse in the cycle. This idea of a wobbling torus connects to a fascinating property of black holes, frame dragging. According to general relativity, a spinning massive object literally drags the fabric of space-time around with it. The supermassive black hole, even while dormant, is likely spinning at a significant fraction of the speed of light. This rotation creates a powerful vortex in space-time that could be physically forcing the inner accretion disk to precess, meaning its axis of rotation slowly circles around over time. This precession would act as an incredibly precise cosmic metronome, governing the timing of the oscillations and creating the stable rhythm we observe from hundreds of millions of light-years away. The detection and study of this oscillation provide a powerful new tool for probing the immediate environment of a black hole without the blinding glare of full-blown accretion. The frequency of the pulse tells us about the scale of the region where it's occurring. The closer to the black hole, the faster the dynamics. The amplitude of the signal gives clues about the amount of mass involved in this final, slow dance. By analyzing this rhythm, astronomers can effectively map the geometry of the emptiness around the black hole, inferring the size and tilt of that inner torus and even estimating the spin rate of the black hole itself. This faint heartbeat is a telegram from the edge of eternity, carrying encoded information about the most extreme gravitational environment known to exist. But the gravitational influence of this cosmic giant may extend beyond the bending of light and time, reaching into the very mechanism that drives the expansion of the universe itself. When astronomers measure the velocities at which other galaxies are moving away from us, they rely on a cornerstone of modern cosmology known as Hubble's law. This principle states that, on the largest scales, a galaxy's recession velocity is directly proportional to its distance from us. The farther away it is, the faster it appears to be flying apart from our own. It's the primary evidence for an expanding universe, a uniform stretching of space that should apply everywhere. However, in a shell of space surrounding NGC 4889, this fundamental law appears to break down. Galaxies at a certain distance from this supergiant are receding at velocities that are subtly but significantly different from what Hubble's law predicts, creating a distinct and anomalous repulsion zone that defies easy explanation. This isn't a simple case of gravitational attraction slowing a galaxy down. That would be expected and is observed in dense clusters due to their mutual pull. What is being detected here is the opposite, an apparent excess of repulsive force acting on galaxies in a specific region around NGC 4889, making them fly away faster than they should. It's as if the fabric of space itself in this zone is stretching more aggressively, adding an extra push to the galaxies within it. This effect is incredibly localized, centered on the galaxy and fading with distance, which immediately points the finger at something associated with the supergiant itself rather than a large-scale fluctuation in the cosmos. The most tantalizing and unsettling hypothesis is that we are witnessing a localized variation in the effects of dark energy, the mysterious force responsible for the universe's accelerating expansion. Dark energy is traditionally thought to be a property of space itself, a constant energy inherent to the vacuum that exerts a negative pressure, causing the expansion to speed up. The key assumption is that this energy density is uniform across the entire universe, the same here, there, and everywhere. The anomaly around NGC 4889 challenges that core assumption head-on. It suggests that in this particular region of extreme mass and gravity, the behavior of dark energy might be different. One compelling theory is that the immense mass of the galaxy and its environs could be interacting with whatever field is responsible for dark energy, suppressing its repulsive effect or altering its properties. If the galaxy's gravity is somehow diluting the dark energy density in its immediate vicinity, it would create a gradient. Galaxies just beyond this suppressed zone would then feel the full, unadulterated force of dark energy from the outside, while still being less held back by the galaxy's gravity, resulting in a net effect that makes them appear to be pushed away faster. Another fascinating possibility moves beyond dark energy entirely and into the realm of unknown physics. Could the supermassive black hole's past activity have left behind a relic field, a kind of energy imprint on space-time that creates a repulsive force? Or perhaps the sheer density of the galaxy is triggering a phase transition in the quantum vacuum around it, effectively changing the rules of empty space and creating a new, temporary form of repulsion. These are highly speculative ideas, but they underscore how an observation like this can force scientists to consider possibilities that lie outside the standard model of cosmology. Of course, extraordinary claims require extraordinary evidence, and astronomers are diligently working to rule out more mundane explanations. Could this be a complex illusion caused by the intricate gravitational lensing we discussed earlier, where the light paths from background galaxies are so warped that it distorts our measurement of their velocities? Or is it a result of the dark matter distribution being so unusual around this galaxy that it is skewing our calculations of the true distances and motions? These are the questions currently being debated, with teams of researchers using ever more sophisticated simulations to try and replicate the observed anomaly. The existence of this potential dark energy repulsion zone is more than just another strange phenomenon. It strikes at the heart of our understanding of the universe's ultimate fate. If dark energy is not a perfect cosmological constant, if it can vary from place to place based on local conditions, then our projections for the far future of the cosmos could be completely wrong. The great emptiness that awaits might not be uniform. This single observation around a single galaxy opens a door to a vastly more complex and dynamic picture of cosmic evolution, where the very energy of nothingness can be shaped by the somethingness of a galactic giant. We now turn our attention from the subtle pulse of the core to a far more visible, yet equally mysterious feature, the galaxy's magnetic personality. Space is threaded with invisible magnetic fields, and in most galaxies, especially turbulent ellipticals, these fields are a chaotic mess. They're tangled and disordered, shaped by billions of years of stellar explosions, gas flows, and galactic collisions. But around NGC 4889, astronomers have mapped something profoundly different. Instead of a chaotic web, the magnetic fields surrounding this supergiant form vast, coherent structures, distinct geometric shapes like vast arcs, and even spiral patterns that seem to defy the otherwise chaotic nature of such an ancient galaxy. It's as if a cosmic artist has taken a brush to the void and painted lines of magnetic force with impossible precision. This discovery is baffling because magnetism on a galactic scale is not a static thing. It's a dynamic force that requires constant energy to maintain its structure against the tendency to decay into disorder. In a spiral galaxy like our Milky Way, the orderly rotation of the galaxy itself can shear and stretch magnetic fields, organizing them along the spiral arms. But NGC 4889 is an elliptical galaxy. It doesn't rotate in an orderly way. Its stars move in random, buzzing orbits, creating a gravitational environment that should churn and shred any large-scale magnetic structure. The presence of these serene, geometric patterns in such a turbulent realm is like finding a perfectly arranged formal garden in the middle of a hurricane. It shouldn't be possible, and yet there it is. So how could such organization emerge from the chaos? One leading theory points back to the galaxy's explosive past and its supermassive black hole. During its active quasar phase, the jets erupting from the black hole would have been carriers of incredibly powerful, organized magnetic fields. As these jets plowed outwards for millions of years, they could have acted like a loom, weaving these imported magnetic fields into the intracluster medium and painting vast, coherent patterns onto the fabric of space itself. The incredible stability of these magnetic fossils suggests they were literally frozen into the hot plasma of the cluster gas, creating a permanent magnetic imprint that has persisted long after the jets that created them fell silent. We would be looking at the lingering signature of the black hole's most powerful outburst, a ghostly magnetic sculpture frozen in time. An alternative and equally fascinating idea involves the galaxy's history of cannibalism. When galaxies merge, their magnetic fields don't just cancel each other out. They can interact, amplify, and even reorganize. It's possible that the precise, geometric patterns we see today are the result of a particularly neat and tidy galactic merger billions of years ago, where the magnetic fields of two galaxies aligned and reinforced each other in a specific way, creating a new, stable composite field. This would be a rare and delicate cosmic dance, requiring a very specific set of conditions, but in a universe as vast and old as ours, even rare events can occur. The magnetic field would then be a living fossil, a preserved record of that one specific ancient collision that shaped the galaxy's destiny. The implications of these magnetic mysteries reach far beyond mere curiosity. These organized fields play a crucial role in shaping the future evolution of the galaxy and its environment. Magnetic fields can channel the flow of hot gas, influence the formation of new stars, and even guide the propagation of high-energy cosmic rays. The presence of such a strong, coherent magnetic architecture around NGC 4889 means it exerts a silent but powerful influence on everything around it. It could be preventing stray gas from falling in and reigniting the central black hole, or it might be protecting the galaxy from the full brunt of the cluster's hot wind, acting as an invisible magnetic shield. Studying this phenomenon is a Herculean task. Mapping magnetic fields across such vast distances requires observing the polarization of light from thousands of background radio sources, building up a statistical picture of how the light's orientation has been twisted by the invisible magnetic forces it passed through. Each new data point is like a single stitch in a colossal tapestry, and the emerging picture is one of breathtaking complexity and unexpected order. These magnetic field anomalies remind us that the universe is not just governed by gravity and mass. The invisible force of magnetism also plays a profound role in writing the rules of cosmic evolution, and in the shadow of this giant, it is writing those rules in a language of strange and beautiful geometry. Now we shift our focus from the subtle fields and forces within the galaxy to the high-energy bullets it seems to be firing across the universe. From the general direction of NGC 4889, our detectors on Earth and in orbit have recorded a persistent and puzzling barrage of ultra-high-energy cosmic rays. These are not mere particles of light or simple electrons. They are atomic nuclei, often protons, or the nuclei of heavier elements like iron hurtling through space at velocities fantastically close to the speed of light. Each one carries the kinetic energy of a well-thrown baseball, but compressed into a single subatomic projectile. This immense energy is the mystery. While our galaxy and others produce cosmic rays, there is a clear and significant excess of these ultra-high energy particles coming from this particular region of space, an excess that our current models of particle acceleration simply cannot explain. The process of creating such powerful particles is one of the great challenges in astrophysics. Normally, we can account for cosmic rays through known, albeit violent, processes. A supernova explosion, for instance, can act as a natural particle accelerator. Its expanding shock wave can boost particles to tremendous speeds, like a cosmic surfboarder catching an incredibly powerful wave. However, even the most spectacular stellar death falls short by orders of magnitude when it comes to generating the energy levels we're detecting from the direction of NGC 4889. The shock waves from a supernova simply aren't powerful enough to impart that much energy to a single particle. This leaves scientists with a compelling question. What kind of cosmic engine operating within or around this galaxy possesses the ferocious power to accelerate matter to such an extreme? All eyes naturally turn to the supermassive black hole, not in its current dormant state, but in its glorious and violent past. Its previous existence as a hyperactive quasar is the most likely suspect for an engine of this magnitude. During that phase, the relativistic jets blasting from its poles would have been perfect natural particle accelerators. These jets are not smooth flows. They are filled with turbulent magnetic fields and immense shock waves. A stray proton or atomic nucleus caught in this maelstrom could be bounced back and forth across a shock front countless times, gaining a tremendous boost in energy with each pass until it is finally flung out into intergalactic space like a bullet from a rifle. The sheer scale and power of those ancient jets could potentially account for the energies we observe, suggesting we are being struck by the lingering artillery shells from a battle that raged millions of years ago. Yet, even this dramatic explanation may not be sufficient. The extreme distance to NGC 4889 presents a serious problem for this theory. Ultra-high energy cosmic rays are not like photons of light that travel in straight lines unaffected. Because they are charged particles, their paths are bent and twisted by the magnetic fields that permeate the space between galaxies. Over a journey of 300 million light-years, even an incredibly powerful magnetic field would cause such a particle to veer wildly off course, making it nearly impossible to trace its origin back to a single, precise point like NGC 4889. The fact that we still see a statistically significant excess from its general direction implies the source must be truly monstrous, producing these particles in such overwhelming numbers that even after their paths are scrambled, a clear signal still shines through. This difficulty has led physicists to consider even more exotic possibilities. One compelling theory involves the decay or annihilation of hypothetical superheavy dark matter particles. It's thought that in the earliest moments of the universe, a population of incredibly massive exotic particles may have been created. These particles would be far heavier than any known particle, and they could have accumulated in the immense gravitational well of NGC 4889, forming a dense cloud around its core. If two of these particles were to collide and annihilate, they could release a tremendous burst of energy, creating a shower of standard model particles that includes these ultra-high energy protons and nuclei. In this scenario, the galaxy itself wouldn't be actively accelerating particles. It would instead be the site of a continuous demolition derby of invisible, ancient matter, with the cosmic rays as the detectable debris from those collisions. Another frontier idea points toward defects in the very fabric of space-time itself. Some grand unified theories in particle physics predict that as the early universe cooled, cracks or imperfections could have formed in the structure of reality, akin to cracks forming in ice. These cosmic defects, known as topological defects, could be reservoirs of immense energy. If one such defect were to decay or collapse near NGC 4889, it could release its stored energy in a cataclysmic burst, creating particles with energies that dwarf anything our conventional astrophysics can produce. This would be an event of truly fundamental significance, a glimpse into the physics of the universe's first moments, with the galaxy serving as the backdrop for this primordial phenomenon. Each of these ultra-high energy particles that strikes our atmosphere is a messenger carrying with it information about the most violent processes in the cosmos. Detecting them is a feat of ingenuity, requiring vast arrays of sensors on the ground to measure the extensive air showers they create upon impact. The mystery of their excess from this particular galaxy is a stark reminder that our catalogue of cosmic engines is still incomplete. It suggests that within the depths of NGC 4889, or in the space it dominates, a powerful and perhaps unknown physical process is still at work, capable of feats of particle acceleration that push the very limits of what we believe is possible. Even in the profound silence that now defines its core, the central black hole of NGC 4889 appears to be sending out faint, ghostly echoes of its past fury. Astronomers have managed to detect ethereal, wispy structures stretching away from the galaxy, the remnants of jets that once blazed with the power of 1 billion suns. These are ghost jets lingering long after the energetic engine that created them has fallen into its deep slumber. Their continued existence is a profound cosmic puzzle, raising a compelling question. How can these structures persist and even emit faint radiation when the central black hole shows no signs of the active feeding needed to power them? The formation of these colossal jets is typically a direct result of a voracious appetite. When a supermassive black hole actively consumes matter, the incredible forces involved can launch a fraction of that material away at nearly the speed of light, focused into two opposing beams. These jets can stretch for millions of light years, and when they are active, they are among the brightest objects in the universe. The ghost jets around NGC 4889 are the faded afterglow of such an event, the dying embers of a fire that once raged uncontrollably. But embers eventually cool, and without a constant source of new energy, they should have faded into complete darkness eons ago. The fact that we can still detect them means some process, however subtle, is still at work. One leading theory suggests we are witnessing the incredibly slow dissipation of energy within the jets themselves. Imagine turning off a powerful spotlight but continuing to see a faint glow from the superheated filament as it cools. On a galactic scale, the particles within these jets were accelerated to such fantastic speeds that they are still traveling outward, and the magnetic fields woven through them are still extremely powerful, though slowly decaying. This residual energy could be enough to produce the faint synchrotron radiation we detect, a last, long sigh from a structure that was built with unimaginable power. The jets are, in effect, coasting on the momentum imparted to them millions of years ago, their gradual fading a testament to the sheer intensity of their initial launch. However, the sheer longevity of this faint emission suggests that simple coasting might not be the full story. Another fascinating possibility involves the jets interacting with the intracluster medium, the superheated gas that fills the space between galaxies in the Coma Cluster. As these ghostly structures slowly plow through this thin but present medium, the interaction itself could generate fresh energy. It's analogous to a spacecraft re-entering Earth's atmosphere. The friction with the air creates intense heat and light, even though the spacecraft's engines are off. In this case, the collision between the relativistic particles in the jet and the protons of the intracluster medium could generate just enough ongoing emission to explain the jet's persistent, if faint, visibility. Perhaps the most intriguing explanation involves a trickle-down effect from the galaxy's surroundings. While the central black hole may not have a proper, bright accretion disk, it is almost certainly still gathering a minuscule amount of material from its environment, perhaps from the stellar winds of old stars or the occasional disrupted dwarf galaxy. This trickle of fuel would be far too little to restart the full quasar engine, but it might be just enough to create a weak, tenuous flow onto the black hole. This feeble accretion could generate enough energy to faintly energize the base of the old jet channels, like a pilot light that's too weak to ignite the main burner but still casts a faint glow. This would mean the ghost jets are not entirely relics. They are being very faintly reignited, a whisper of the roar that once was. The detection and study of these ghost jets provide a unique opportunity for astronomers. They act as a fossil record, preserving the direction and power of the black hole's past outburst. By analyzing their structure and spectrum, scientists can work backwards to calculate the total energy the black hole released during its active phase, helping to piece together the historical timeline of the entire galaxy. Furthermore, they serve as a natural laboratory for studying the physics of how such relativistic structures evolve and interact with their environment over timescales that are impossible to replicate in any simulation. These faint echoes from a dormant giant are a powerful reminder that even in cosmic retirement, the past is never truly gone. It simply fades to a whisper, waiting for us to listen closely enough to hear its story. Now we arrive at a phenomenon that connects the silent tremors of this distant galaxy to the very fabric of the cosmos itself. Across the globe, incredibly sensitive observatories have begun to detect a faint, persistent hum, a gravitational wave background that permeates all of space. This isn't the signal of a single cataclysmic event, but the combined rumble of countless black hole and neutron star mergers happening across the universe throughout time. It's the universe's deepest, most fundamental frequency, and when astronomers began to analyze this hum, they discovered something deeply puzzling. A strange, recurring correlation between subtle fluctuations in this background signal and periodic energetic events emanating from the direction of NGC 4889. It's as if the galaxy's own rhythm is somehow leaving a faint imprint on the gravitational waves that wash through the cosmos. This correlation is so counterintuitive it challenges our basic understanding of how gravitational waves are generated. We believe these ripples in space-time are created by the most violent, asymmetric events in the universe, the in-spiral and collision of two incredibly dense objects like black holes. These are singular, catastrophic explosions of gravitational energy. The idea that a single, mostly dormant elliptical galaxy could be contributing a continuous, periodic signal to this universal background is completely unexpected. It suggests a mechanism for generating gravitational waves that is both ongoing and strangely orderly, a process that operates on a timescale of months or years rather than the fraction of a second it takes for two black holes to merge. This isn't a cannonball splash in the fabric of space-time. It's a slow, rhythmic pulsing. One compelling theory attempts to link this signal back to the galaxy's faint but detectable core oscillation, its slow heartbeat. The theory proposes that the wobbling, precessing torus of material around the central black hole is not just emitting light, but is also massive enough to be a potent source of gravitational waves. As this vast structure wobbles, its asymmetric mass distribution could be constantly rippling space-time, sending out a continuous, low-frequency gravitational wave signal with the same periodicity as the observed oscillations. While the emission from any single structure would be incredibly faint, the sheer scale involved, a structure likely encompassing billions of miles, could make it just powerful enough to be teased out of the background data as a correlated signal. Another, more speculative idea involves the galaxy's vast population of binary white dwarf stars. Elliptical galaxies like NGC 4889 are known to contain millions of these ancient stellar embers, and many are locked in binary orbits. While a single binary white dwarf system generates gravitational waves far too weak to detect individually, the combined chorus of millions of them, all orbiting in sync with the galaxy's own mysterious rhythm, could theoretically create a coherent, enhanced signal. If some unknown influence, perhaps the galaxy's overall gravitational field or its magnetic environment, has somehow synchronized the orbits of these binaries, their collective hum could be amplified, making this galaxy stand out against the cosmic background in a unique way. The most profound implication of this correlation is that we might be discovering a whole new class of gravitational wave sources, Until now, our focus has been on the loud, transient events. But this suggests that quieter, continuous processes within galaxies could also contribute to the gravitational wave background in significant and previously unimagined ways. It opens up the possibility of using gravitational waves not just to study collisions, but to probe the internal dynamics and structure of galaxies themselves. The faint, rhythmic pulse from NGC 4889 could be the first hint of an entirely new field of gravitational wave astronomy, one that listens to the slow, steady heartbeat of galaxies rather than just their violent death throes. Surrounding most large galaxies, including our own Milky Way, is a vast and ancient swarm of globular clusters. These are dense, spherical collections of hundreds of thousands of stars, some of the oldest structures in the universe, and they act as faithful satellites orbiting their host galaxy. For a galaxy of NGC 4889's immense size and mass, astronomers expected to find a truly staggering number of these stellar beehives. Predictions ran into the tens of thousands. Yet, when they counted, the numbers fell dramatically short. The galaxy is missing a significant portion of its expected globular cluster population, a cosmic robbery that points to a violent and tumultuous history, even for a place already defined by mystery. The fate of these missing clusters likely lies in the extreme environment of the dense Coma Cluster itself. Imagine a crowded downtown square during a busy rush hour. The constant jostling and bumping is relentless. For a galaxy like NGC 4889, moving through the crowded core of the cluster, the gravitational interactions with hundreds of other galaxies are a constant fact of life. This creates a process known as tidal stripping. As a globular cluster on a wide orbit swings around its host galaxy, the combined gravitational pull of a passing neighbor can literally pluck it away. The cluster isn't destroyed in a collision. It's gently but firmly pulled from NGC 4889's grasp and sent drifting into the intracluster medium, eventually becoming a free-floating cluster belonging to the entire cluster rather than any single galaxy. Over billions of years, this relentless harvesting could have stripped away a vast number of these ancient stellar systems. Another, even more destructive process is tidal shocking. When a globular cluster passes particularly close to the dense core of its host galaxy, it doesn't experience a steady pull but a sharp, intense gravitational shock. This is especially potent near the supermassive black hole, where the gravitational gradients are unimaginably steep. This shock can violently perturb the orbits of stars within the cluster, effectively shaking it apart from the inside. The stars are pulled out of the cluster's grip one by one, adding to the general halo of the galaxy and leaving behind nothing but a diffuse cloud of stars where a tight-knit community once thrived. The immense central mass of NGC 4889 makes it a particularly efficient destroyer of clusters through this mechanism. There's also the possibility of direct collisions and mergers between the globular clusters themselves. In the crowded central regions of the galaxy, the density of these clusters would have been incredibly high in the distant past. Just as galaxies can merge, so too can these smaller stellar systems. When two globular clusters collide, they don't necessarily form a larger, new cluster. Instead, the interaction can be chaotic, stripping stars away from both and creating a diffuse stream of stars that eventually disperses into the galaxy's halo. This process of destructive merging could have steadily reduced the total number of clusters over time, consolidating their stars into the general population of the galaxy. The missing globular clusters are more than just an absent population. They are a key piece of archaeological evidence. Their absence tells a story of a galaxy that has lived a far more violent and interactive life than most. It suggests that NGC 4889 has spent eons in the rough and tumble downtown core of the Coma Cluster, subjected to constant gravitational harassment that has slowly robbed it of its entourage. This history of stripping and destruction aligns with the other puzzles we've seen, painting a picture of a galaxy that has been shaped and reshaped by its extreme environment, leaving behind the enigmatic giant we observe today. Perhaps the most mind-bending of all the phenomena we've encountered so far is a discovery that seems to blur the line between the infinitesimally small and the astronomically large. In the outer halo of NGC 4889, astronomers have observed pairs of stars on diametrically opposite sides of the galaxy that exhibit a bizarre and deeply puzzling synchronization. Their light properties, specifically their polarization and certain spectral features, appear to be linked in a way that defies any classical explanation. This coordinated behavior bears a startling resemblance to a phenomenon we've only ever witnessed in controlled laboratory experiments on Earth: quantum entanglement. The suggestion that this spooky connection, as Einstein famously called it, could be operating on a scale of hundreds of thousands of light years is so radical that it challenges the very foundations of our understanding of physics. To grasp why this is so revolutionary, we need to understand what quantum entanglement is in its normal, tiny domain. At the subatomic level, two particles like a pair of photons can become linked or entangled. After that connection is forged, measuring a property of one particle, such as its spin, will instantly determine the corresponding property of its partner, no matter how far apart they are separated. This spooky action at a distance violates our classical intuition about how the universe should work, where information cannot travel faster than light. Yet, it's a well-documented and fundamental part of quantum mechanics. The critical point is that this effect is incredibly fragile. In the lab, we go to extraordinary lengths to shield entangled particles from any interaction with their environment, because even the slightest disturbance will break the delicate quantum link, a process known as decoherence. The idea that such a fragile connection could not only form but persist between two stars separated by an entire galaxy, bathed in the radiation and gravitational noise of billions of other stars, seems almost impossible. So what is the actual evidence that has sparked this controversial discussion? It doesn't come from a single observation, but from a statistical analysis of starlight. Researchers meticulously studied the light from thousands of widely separated stellar pairs in the galaxy's halo. They were looking for correlations that couldn't be explained by common origin or any known physical process that transmits influence at or below the speed of light. In a small but statistically significant number of these pairs, they found just that. The polarization planes of the light from these stars showed a degree of alignment far exceeding what random chance would allow. Furthermore, subtle, simultaneous fluctuations in their spectra occurred more often than any conventional astrophysical model could account for. It's as if these stars, though separated by a gulf of space that would take light hundreds of thousands of years to cross, are somehow still whispering to each other. The immediate and most logical rebuttal from the scientific community is that this is a case of mistaken identity, an illusion created by our limited perspective. Perhaps these seemingly connected stars aren't independent at all, but are linked by vast, invisible structures we simply cannot see. Could immense magnetic fields stretching across the galaxy be synchronizing the behavior of the plasma around these stars in a way that mimics quantum correlation? Or is this the signature of some unknown type of dark matter interaction, a hidden force that connects visible matter across vast distances without our knowledge? These are the more conservative and therefore more favored explanations that physicists are actively exploring before leaping to a conclusion as monumental as galactic scale entanglement. Yet, if further evidence continues to point toward a genuinely quantum explanation, the implications would shake physics to its core. It would suggest that the phenomenon of quantum entanglement is not confined to the microscopic world, but is a universal property that can scale up, appearing in systems of any size under the right conditions. This would force a complete rethink of the boundary between the quantum and classical worlds. How could such a delicate state survive the brutal decoherence that should be caused by the gravitational tides, radiation pressure, and constant interaction with other particles present in a galactic environment? The answer might lie in the nature of the stars themselves. Perhaps these are not ordinary stars, but ancient stellar remnants like white dwarfs or neutron stars whose incredibly dense, ordered interiors could somehow protect and preserve a quantum connection formed in their distant past. Another extraordinary possibility is that we are not seeing entanglement between the stars themselves, but between their underlying space-time coordinates. The immense mass of NGC 4889 warps the fabric of the universe around it so severely that it might be creating a unique environment where the rules are different. In this scenario, the entangled property isn't a characteristic of the star's light, but of their very position in the gravitational field, a connection woven into the curved geometry of space-time itself by the galaxy's monstrous gravity. This would represent a previously unknown marriage between general relativity and quantum mechanics, a glimpse of the holy grail of physics, a theory of quantum gravity. Whether this controversial signature holds up to further scrutiny or is eventually explained by more conventional means, its investigation is pushing the limits of astrophysics and quantum theory. It forces us to ask profound questions about the interconnectedness of the universe and whether the quantum weirdness that defines the tiny world of particles also plays a hidden role in governing the grand architecture of galaxies. The potential discovery of large-scale entanglement would be a paradigm shift of epic proportions, suggesting that the universe is far more deeply and strangely connected than we ever dreamed. Even light itself seems to obey unfamiliar rules in the shadow of this galactic giant. Astronomers have documented a series of strange and delayed flashes, light echoes emanating from the depths of NGC 4889 that tell a story which doesn't quite make sense. A light echo occurs when a sudden, brilliant flash of light, like a stellar explosion, illuminates vast clouds of dust and gas in its vicinity. The light travels directly to us, but also outward to these distant clouds, which then reflect it back toward our telescopes like cosmic mirrors. We see the initial flash, and then, years or even decades later, we see the reflected echo. It's a well-understood phenomenon, a kind of cosmic bounce that allows us to study the aftermath of an event long after the original fire has faded. But around this supergiant galaxy, the echoes are arriving from all the wrong places. The mystery lies in the geometry. By carefully measuring the time delay between the initial flash and its echo, astronomers can calculate the precise distance the light traveled to the reflecting cloud and then back to us. This allows them to triangulate the cloud's exact location in three-dimensional space. On multiple occasions, observations have revealed a deeply puzzling result. The echoes are appearing to originate from vast clouds of dust that, according to this triangulation, are simply not there. The calculated positions point to regions of empty space far from any known nebula or gas structure. It's as if invisible mirrors are hanging in the void, catching light from ancient cataclysms and throwing their reflection back at us on a delay, defying every attempt to locate the reflecting surface. This bizarre mismatch points toward one overwhelming culprit: complex gravitational lensing on a scale and of a complexity we have not yet mastered. We know the galaxy's immense mass warps the space around it, creating a natural lens. But the anomalous light echoes suggest this lensing is far more intricate than our models account for. The most likely explanation is that the path of the echo light is being bent and folded by the gravity of unseen concentrations of mass, perhaps those elusive dark matter subhalos we discussed earlier. The light from a flash might travel out to a dust cloud we can see, but on its journey back to us, its path is severely deflected by one of these invisible clumps. To an observer on Earth, this deflection makes it appear as though the echo originated from a completely different point in space, a phantom reflection from a cloud that does not exist. Our current lensing models are good, but they are not yet perfect enough to untangle this specific light path and pinpoint the true, hidden lens responsible for the deception. Another, more speculative possibility involves the geometry of the dust clouds themselves. Perhaps the reflecting structures are not simple, distant sheets of dust, but are instead incredibly complex and porous fractal formations like cosmic sponges with deep cavities and tunnels. Light could enter these cavities, bounce around internally multiple times, and then exit after a significant delay and from an unexpected angle. This would create the illusion of an echo coming from a void, when in reality it was merely the final exit point from a labyrinthine structure we cannot resolve with our current telescopes. The echo would be a trick of celestial architecture, a hall of mirrors on an interstellar scale. There is also a chance we are witnessing the echo of a single event being lensed multiple times. If the original flash was gravitationally lensed itself, split into multiple images by the galaxy's warped space-time, then each of those images could be illuminating different dust clouds at different times. An echo from one of those secondary images could easily appear to come from a nonsensical location if we don't account for the entire, convoluted journey the light has taken. We will be trying to solve a puzzle without knowing that the initial picture had already been fractured and rearranged. Studying these wayward echoes is more than an exercise in cartography. It's a powerful new tool for probing the invisible. Each anomalous echo is a single data point tracing out the path that light took through the galaxy's gravitational field. By collecting enough of these errant signals, astronomers can perform a kind of reverse engineering, using the light's path to map the precise distribution of mass, both visible and dark, that it encountered along the way. These photons have acted as fearless explorers, traveling through the most warped regions of space and returning with encoded information about the hidden structure of the galaxy. Their confusing stories are forcing us to draw a more detailed and accurate map of the true mass of NGC 4889, revealing the ghostly contours of the dark matter we cannot see by any other means. Flowing through the immense gravitational field of NGC 4889 are not just stars and gas, but vast, invisible rivers of dark matter. These are not static halos, but dynamic streams, filaments of the unseen substance that are predicted to flow through galaxies and between them, remnants of the cosmic web from which all large-scale structure formed. According to our best models, these streams should pass through the visible matter of a galaxy like ghosts walking through walls, their gravitational influence smooth and predictable, exerting a pull but otherwise not interacting with the stars and gas they permeate. Yet, around this supergiant galaxy, astronomers are detecting subtle gravitational anomalies that suggest this isn't the case. The streams appear to be interacting with the visible galaxy in strange, unpredictable ways, as if dark matter is not the utterly passive substance we have always assumed it to be. The evidence for this unexpected interaction comes from meticulously mapping the motions of stars within the galaxy's vast halo. By measuring the tiny, precise velocities of thousands of individual stars, scientists can create a detailed chart of the gravitational forces acting upon them. What they have found are peculiar, localized disruptions in these motions. In specific regions, stars are moving with slight but statistically significant deviations from the smooth flow expected from the combined gravity of the visible mass and a smoothly distributed dark matter background. It's as if these stars are experiencing an additional, unexpected tug, or in some cases, a slight push. The pattern of these disruptions often correlates with the predicted paths of major dark matter streams flowing into the galaxy from the wider cluster environment, suggesting the streams themselves are the source of the anomalous forces. This presents a profound challenge to the standard model of cold, collisionless dark matter. For decades, the defining characteristic of dark matter has been that it interacts with normal matter and with itself only through gravity. It does not feel electromagnetic forces, meaning it cannot crash, bump, or create friction like normal particles. It should simply flow through everything, its gravity the only sign of its presence. The apparent interactions seen in NGC 4889 hint that this might not be the complete picture. Perhaps dark matter particles can interact with each other through some unknown force other than gravity, a force that allows them to clump and structure themselves within the streams in ways that create more complex gravitational signatures. Or perhaps there is a minuscule but non-zero interaction between dark matter and normal matter that only becomes detectable in areas of extremely high density, like within these focused streams. One compelling theory to explain these observations is the presence of dense knots or subhalos within the dark matter streams themselves. If dark matter has some capacity for self-interaction, even a very weak one, it could allow these streams to fragment and form ultra-dense clumps as they are stretched and compressed by the galaxy's gravity. These invisible knots would then exert a stronger gravitational pull on nearby stars than the diffuse stream would, creating the precise localized velocity deviations that astronomers are detecting. We would be seeing the gravitational footprints of dark matter icebergs drifting within an invisible river. Another, more radical idea involves a phenomenon called dynamical friction. This is a well-understood process for normal matter. As a massive object like a star cluster moves through a cloud of stars or gas, its gravity pulls the background particles toward it, creating a wake of denser material behind it. This wake then gravitationally tugs back on the massive object, slowing it down. It's a form of gravitational drag. This effect should be negligible for dark matter, as its particles are not supposed to congregate into such wakes. However, if the dark matter streams are causing measurable changes in the motion of stars, it could be a sign that the reverse is also true. The collective gravity of the stars is somehow imparting a drag on the dark matter stream itself, subtly altering its flow and evolution in a way that betrays an unexpected level of interaction. The implications of these potential interactions are enormous. If dark matter can form denser structures within streams than previously thought, it would completely change our understanding of how galaxies assemble and grow. These dense clumps would sink to the center of a galaxy more efficiently, potentially explaining how supermassive black holes grew so large so quickly in the early universe. Furthermore, it would provide crucial clues for physicists searching for dark matter particles here on Earth. Detecting a particle that interacts with nothing is nearly impossible, but detecting one that has even a tiny probability of interacting with itself or normal matter gives experiments a specific, narrow window to look through. The strange flows within NGC 4889 could be providing the first observational hints of exactly what that window might be. But perhaps the most persistent and fundamental tool in an astronomer's kit is also the one behaving most strangely around this cosmic giant. When we point our spectrographs at NGC 4889, we are listening to the ancient song of its starlight, analyzing the specific frequencies to understand its composition, temperature, and most importantly, its motion. This is done by measuring the Doppler shift, the stretching or compressing of light waves as an object moves away from or toward us. A shift toward the red end of the spectrum means the object is receding. A shift toward blue means it is approaching. It's a reliable cosmic speedometer we've used for over a century. Yet, when applied to different regions of this supergiant galaxy, this trusted tool returns a set of readings that are not just confusing, but fundamentally contradictory, creating a spectral line shift paradox that challenges our very understanding of how this galaxy moves and evolves. The paradox emerges from a detailed velocity map of the galaxy. In a typical rotating system like a spiral galaxy, we expect a clear and consistent pattern. One side should show a uniform redshift as it spins away from us, while the opposite side shows a uniform blue shift as it spins toward us. But the data from NGC 4889 reveals no such order. Instead, we see a chaotic patchwork. Sectors of stars on the side that should be universally receding are instead hurtling toward us at fantastic speeds, while other sections on the approaching side are stubbornly moving away. These aren't small discrepancies, they are major velocity anomalies that completely contradict any model of simple, orderly rotation. It's as if the entire galaxy is not spinning like a wheel, but churning like a boiling pot, with massive currents of stars moving in wildly different directions simultaneously. This bizarre internal motion immediately rules out the possibility of NGC 4889 being a relaxed, settled system. The chaotic velocity field is a clear signpost of a very recent and very violent past. The most widely accepted explanation is that we are witnessing the ongoing digestion of a major galactic merger. Billions of years ago, another large galaxy likely collided with and was swallowed by this supergiant. But the process is not yet complete. The stars from the devoured galaxy haven't had time to settle into a new, harmonious orbit. They are still swarming through their new home on chaotic, intersecting paths like a beehive that's been kicked over. This would naturally create the observed patchwork of redshifts and blueshifts, as different streams of stars from the merger remnant carry the momentum of their original, now destroyed galaxy. However, the sheer scale and power of the anomalies have led some scientists to consider an even more exotic possibility. Could the paradox be due not to the motion of the stars, but to something affecting the light itself on its long journey to Earth? The light from NGC 4889 must travel through 300 million light-years of expanding space and through the immense gravitational field of the galaxy itself and the Coma Cluster. What if our assumptions about how that journey affects the light are incomplete? General relativity tells us that light loses energy and is redshifted as it climbs out of a gravitational well. The extreme and uneven distribution of mass within this galaxy, including its vast and potentially lumpy dark matter component, could be creating a complex landscape of gravitational redshifts that is imprinted on top of the Doppler shift from the star's motions. We might be seeing a combined signal where the true velocity of the stars is masked by the warping of space-time they are embedded within. Untangling this effect would be like trying to hear a single conversation in a roaring stadium. This leads to the most speculative but fascinating interpretation of all. A few physicists have proposed that the contradictory shifts could be a hint of something beyond our current gravitational models. Perhaps in regions of such extreme density, the very constants of nature like the speed of light or the behavior of gravity itself could vary minutely. If true, this would mean the spectral lines we are measuring are not just being shifted by motion and gravity, but their very nature is being subtly altered at the source, creating a false signal that we misinterpret as motion. While this remains a fringe idea, it underscores how a persistent, high-quality paradox like this can force us to question the most fundamental pillars of our understanding. The spectral lines from NGC 4889 are not just telling us about the speed of stars, they are asking us if we truly understand the rules of the cosmos in which those stars exist. Deep beneath mountains and buried in Antarctic ice, some of the most sensitive scientific instruments on Earth are constantly listening. They aren't tuned to sound, but to the faintest whispers of the most ghostly particles in the universe, neutrinos. These nearly massless entities, born in the hearts of stars and the aftermath of cosmic cataclysms, stream through our planet by the trillions every second, barely interacting with anything. They are the universe's most elusive messengers, and they carry information from the most extreme environments imaginable. When physicists began meticulously mapping their origins, they noticed a faint but persistent and deeply puzzling signal. An excess of the highest energy neutrinos ever recorded seemed to be coming from the general direction of the Coma Cluster, and by extension, the supergiant galaxy anchoring it, NGC 4889. This detection is more than just another anomaly. It is a direct telegram from the galaxy's most violent hidden engines, written in a language we are only just beginning to understand. The mystery lies in the sheer power these neutrinos possess. Creating a single high-energy neutrino requires a particle accelerator of cosmic proportions. The most common known sources, like the energetic shock waves from supernova explosions or the active cores of distant quasars, simply don't pack enough punch to explain the extreme energies we're detecting from this region. It's the difference between a firecracker and a nuclear bomb. The known sources are the firecrackers, but the signal from NGC 4889 points to something with the yield of a nuclear event. Standard particle physics, which beautifully explains how neutrinos are created in sun-like stars or in our own atmosphere, hits a wall here. The models cannot account for the number of these ultra-powerful particles arriving from this one patch of sky. This forces us to ask what unimaginable engine operating within or around this galactic giant is capable of such phenomenal feats of particle acceleration. The prime suspect, as with so many of this galaxy's mysteries, is its dormant supermassive black hole. While it slumbers now, its past as a hyperactive quasar provides a compelling blueprint for neutrino production. During that violent era, its relativistic jets would have been perfect natural particle accelerators. Within those focused beams of matter and energy, protons could be accelerated to near light speed. If one of these ultra-fast protons were to collide with another proton or a photon in the dense environment near the jet's base, the resulting collision would create a shower of secondary particles, including short-lived particles called pions. When these pions decay, they are a known factory for producing high-energy neutrinos. This process could have created a tremendous burst of neutrinos millions of years ago, a flash in the pan of cosmic time whose faint afterglow we are only detecting now as the particles finally reach our telescopes. However, the continuous nature of the excess presents a problem. A single, ancient burst would have been a one-time event, a neutrino flash that has now passed us by. The fact that we seem to be detecting a steady trickle suggests an ongoing process. This points to a more recent and sustained engine. One fascinating possibility is that the black hole isn't entirely dormant, but is instead experiencing a slow, grinding feast. Even a trickle of material, the shredded remains of a star, or a cloud of gas straying too close spiraling into the void could generate powerful shock waves in the tenuous accretion flow. These shocks could be continuously re-accelerating particles to the tremendous energies required, creating a persistent, low-level neutrino beacon that shines faintly against the cosmic background, a faint but steady hum from a sleeping giant's digestive system. Yet another groundbreaking theory moves beyond conventional astrophysics and into the realm of speculative particle physics. The detected excess could be the signature of something even more profound, the annihilation of dark matter. We believe NGC 4889 sits within a massive halo of this invisible substance. Some theories propose that dark matter is not a single particle, but a whole spectrum, including very heavy particles that could have been created in the earliest moments of the universe. If two of these hypothetical super-heavy dark matter particles were to collide and annihilate within the galaxy's dense halo, the energy released would be tremendous. This annihilation could produce a cascade of standard particles, including a shower of high-energy neutrinos at precisely the energies we detect. If confirmed, this wouldn't just solve the neutrino mystery. It would be the first indirect detection of dark matter's particle nature and a revolutionary window into physics beyond the standard model. Each of these high-energy neutrinos that strikes the ice in Antarctica or the water in the Mediterranean is a fearless explorer. It has traveled for 300 million years, moving in a nearly straight line from its source, unaffected by magnetic fields or interstellar dust that would bend or block light. It arrives at our detectors carrying pure, unaltered information about the extreme environment that created it. The unexplained excess from the direction of NGC 4889 is a siren call, reminding us that even in its apparent quietude, this galaxy harbors engines of immense power capable of fundamental particle creation. The path to understanding them is written in the faintest of signals, requiring us to build ever larger and more sensitive telescopes to decode the messages sent by the universe's most elusive messengers. Woven through the luminous haze of this ancient galaxy's core, astronomers have uncovered structures so strangely familiar they seem almost impossible. Vast filaments of dust and ionized gas stretching for thousands of light years are twisted into a configuration that echoes the most fundamental blueprint of life itself, the double helix. This cosmic DNA pattern, etched on a scale that defies human comprehension, presents one of the most visually stunning and intellectually baffling of all the galaxy's mysteries. How could such an exquisitely organized form emerge from the supposedly random and chaotic environment of a giant elliptical galaxy, a place where orderly structure is thought to have been erased billions of years ago? The formation of these filaments is a story written in magnetic fields and gravitational tides. Unlike the majestic spiral arms of a galaxy like our Milky Way, which are shaped by orderly rotation, this helix is likely the fossilized remnant of a dynamic and violent process. The prevailing theory points directly to the galaxy's supermassive black hole and its past outbursts. During its active quasar phase, the jets erupting from the black hole would have been carrying not just matter and energy, but immensely powerful, organized magnetic fields. As these jets plowed through the surrounding interstellar medium, they would have acted like a cosmic drill bit, spinning and twisting the clouds of gas and dust in their path. The magnetic fields frozen into this plasma could have provided a supporting scaffold, locking the twisted structure in place long after the jets themselves shut down. We would be looking at the ghostly impression of those magnetic field lines, a permanent sculpture carved into the fabric of the galaxy. Another compelling possibility involves a slow, cosmic dance between two galaxies. If a smaller, gas-rich galaxy had a close encounter with NGC 4889, the immense gravitational tides from the supergiant could have begun to stretch and pull the victim apart. If this encounter occurred at just the right angle, with the smaller galaxy moving on a slightly off-center trajectory as it was torn asunder, the pulled-out stream of gas could have naturally gained a rotational spin, twisting into a helical pattern as it was drawn into the larger galaxy's maw. This process would be like watching taffy being pulled and twisted simultaneously, with gravity providing the pull and the orbital dynamics providing the twist, creating a temporary double helix of stellar debris on a galactic scale. The sheer longevity of these structures adds another layer to the puzzle. In the turbulent interior of a galaxy, such delicate formations should be short-lived, shredded apart by the random motions of stars and the shockwaves from supernova within a few million years. The fact that they persist suggests that something is actively holding them together against the forces of chaos. This is where the galaxy's mysterious magnetic personality likely comes back into play. The same coherent magnetic fields that may have helped create the helix could also be acting as a protective sheath, containing and stabilizing the structure against disruption. It's as if the filaments are encased in an invisible magnetic tube that maintains their intricate form against all odds. The implications of this discovery reach far beyond mere celestial curiosity. The presence of such an organized structure challenges the very classification of NGC 4889 as a simple elliptical galaxy. It suggests a far more complex and dynamic history, one involving precise, ordered forces that we typically associate with younger, spiral galaxies. This cosmic DNA pattern forces astronomers to ask whether the ingredients for large-scale order, powerful magnetic fields, specific types of gravitational interactions, can persist and express themselves even in the oldest and most seemingly chaotic environments. It's a powerful reminder that the universe often favors pattern and structure, even in its most violent corners. Ultimately, this galactic double helix serves as a stunning metaphor for the interconnectedness of the cosmos. It mirrors the shape that carries the code for life on our tiny world, reminding us that the same physical laws that govern the spinning of a galaxy also govern the replication of a cell. While it is almost certainly not a literal message or a sign of life, Its existence is a profound illustration that the universe operates with a language of geometry and mathematics that is universal, from the smallest scale to the largest. This pattern is a natural work of art, a spontaneous alignment of physics that creates a form of breathtaking beauty and deep significance, proving that even in the depths of space, nature finds a way to write its signature in a familiar, spiraling script. But now we arrive at one of the most profound and unsettling mysteries of all, a finding that, if confirmed, would force a rewrite of the most fundamental rules of the universe. For decades, the bedrock principle of cosmology has been the assumption that the laws of physics are the same everywhere. The speed of light, the strength of gravity, the charge of an electron, these fundamental constants are believed to be just that, constant. They are the immutable rules of reality, the fixed settings of the cosmos that allow us to understand a quasar billions of light years away with the same physics we use in a laboratory on Earth. Yet, a series of meticulous observations targeting NGC 4889 have thrown this very idea into question, suggesting that in the shadow of this galactic giant, the fine structure constant, a number that governs the strength of electromagnetic interactions, might not be so constant after all. This investigation relies on a technique as elegant as it is powerful. When light from a distant quasar passes through a cloud of gas, certain elements within that cloud absorb very specific wavelengths of that light. The pattern of these absorption lines, etched into the quasar's spectrum like a unique chemical fingerprint, is exquisitely sensitive to the value of the fine structure constant. By comparing the precise spacing of these lines in light that has passed near NGC 4889 to the spacing measured in laboratories on Earth, astronomers can detect even the most minute shifts. And the data hints at a tiny but statistically significant deviation. The lines are not quite where they should be, suggesting that the strength of electromagnetism in that region of space may be ever so slightly different. The immediate and most logical suspicion falls on the immense gravitational field of the galaxy itself. Einstein's theory of general relativity tells us that gravity warps not only space but time, and a severe enough warping could potentially mimic the signature of a changing constant. Perhaps the light's journey through such curved space-time is altering its properties in a way we haven't fully learned to subtract from the signal. It's a complex background effect, a kind of cosmic mirage that must be painstakingly accounted for before any more radical conclusions can be drawn. Teams of researchers are developing increasingly sophisticated models to do just that, trying to determine if the ghost of gravity is playing a trick on our instruments. However, if all conventional explanations are exhausted and the variation holds, the implications are staggering. It would suggest that the very fabric of reality is not uniform, but that the rules of the game can change from one region of the universe to another. One compelling theory links this potential inconstancy to dark energy. The prevailing model holds that dark energy is a property of the vacuum of space itself, a constant energy density. But what if it's not constant? What if dark energy is the manifestation of a dynamic field that can interact with other fundamental forces? In a region of such extreme mass density as NGC 4889, this hypothetical field could be suppressed or altered, causing a local, secondary change in other constants like the fine structure constant. We wouldn't be seeing a change in the law itself, but rather the influence of an unknown interaction between dark energy and electromagnetism. This leads to an even more mind-bending possibility rooted in string theory and other attempts to unify gravity with quantum mechanics. These theories often propose the existence of additional, compactified dimensions of space beyond the three we experience. In such models, the fundamental constants we observe are not primary. They are the result of the size and shape of these hidden dimensions. The idea is that the value of the fine structure constant could depend on the local environment. If the immense mass of NGC 4889 is somehow distorting these extra dimensions in its immediate vicinity, it could subtly alter the constants that emerge from them. The galaxy wouldn't be breaking the laws of physics. It would simply be existing in a slightly different configuration of the multiverse, where the laws have a different set of parameters. The pursuit of this mystery is a testament to the incredible precision of modern astronomy. Detecting such a minuscule potential shift requires comparing observations across the largest distances and timescales imaginable, pushing our technology to its absolute limits. Each new measurement is a vote for or against the uniformity of nature. A confirmed variation would be arguably the most significant discovery in physics in a century, forcing us to abandon the principle of a perfectly uniform cosmos and accept a universe where the rules themselves might be fluid, shaped by location and environment. It would mean that our local physics is not the universal physics, and that in the deep gravitational wells of supergiant galaxies, reality itself might operate by a slightly different set of rules. Gravity is the great architect of the cosmos, the invisible hand that sculpts galaxies and binds stars together. For a structure as colossal as NGC 4889, with a mass hundreds of billions of times that of our Sun, the gravitational pull at its center should be unimaginably intense. Picture a well in the fabric of space-time so deep that light itself struggles to climb out, a cosmic vortex of unbelievable power. This concept is known as the gravitational potential well, and its calculated depth is a direct reflection of the total mass contained within the galaxy. Yet, when astronomers set out to measure the true depth of this well by observing the motions of stars and satellite galaxies, they were met with a result that defied all expectations. The well is there, certainly, but it is far shallower than their equations insisted it should be. It's as if they dropped a plumb line expecting to measure a bottomless chasm, only to find it hit a plateau far sooner than predicted. The galaxy possesses the mass of a leviathan, but the gravitational grip of something far less imposing. This gravity well anomaly forces a fundamental question about what we're actually measuring. The depth of a gravitational well is not dictated by mass alone, but by how that mass is distributed. A simple analogy is to imagine two sacks, each containing 1,000 pounds of material. One sack is filled with a single, incredibly dense ingot of lead, while the other is filled with 1,000 individual 1-pound feathers. While their total weight is identical, their gravitational fields feel completely different. The lead ingot creates a very deep, intensely concentrated well right at its center. The sack of feathers creates a much broader, shallower well, its gravitational influence spread out over a larger volume. The unexpected shallowness of NGC 4889's well suggests its immense mass is not packed into a central singularity, but is instead distributed like the feathers spread throughout an enormous volume of space in a way that prevents the formation of an intensely deep central well. So what mechanism could possibly prevent such a vast amount of matter from collapsing inward under its own weight to form a steeper well? The most compelling answer lies in the chaotic and random motions of its hundreds of billions of stars. Unlike a spiral galaxy like our Milky Way, where stars orbit in a neat, ordered disk, the stars within this supergiant elliptical move on random, buzzing trajectories in all three dimensions. This creates a powerful form of internal pressure that acts against the pull of gravity, much like the frantic motion of molecules in a hot gas prevents it from collapsing. The stars themselves are providing the support structure, their kinetic energy holding the galaxy up and resisting further collapse. This results in a galaxy that is incredibly massive but also incredibly puffy, with its mass spread out over a vast area, which directly translates to a shallower central gravitational potential. This discovery also provides a crucial new piece to the puzzle of the galaxy's missing dark matter halo. The measured shallowness of the gravity well is a direct measurement of the total gravitational force at play. If that force is less than expected from the visible mass, it could mean that a significant portion of the dark matter we assumed was there simply isn't. Or it could mean that the dark matter itself is distributed in an exotic, ultra-diffuse configuration, perhaps stretched into a vast, faint web by the same gravitational interactions that stripped away its globular clusters. The gravity well anomaly isn't just a curiosity. It is a direct probe into the distribution of all mass, seen and unseen, and it suggests that the standard model of a galaxy neatly nestled inside a massive, roughly spherical dark matter halo may be too simple for an environment as extreme as this. Another fascinating possibility is that we are witnessing the aftermath of a phenomenon called violent relaxation. This occurs during a major galactic merger when the gravitational field becomes incredibly chaotic as two galaxies combine. Stars are thrown onto new, random orbits in a process that is anything but gentle. This chaotic scrambling effectively heats up the stellar population, making the resulting galaxy larger and puffier than the sum of its parts. The end product is a galaxy whose stars are so energized that they can support the structure against its own gravity without needing to collapse into a steeper well. The shallowness we measure today could be the permanent signature of a catastrophic merger that took place billions of years ago, a fossilized record of the moment this galaxy digested another and had its inner gravitational landscape forever flattened by the violence of that encounter. This anomaly challenges the very way we calculate mass in the most distant objects in the universe. For decades, we have used the motions of stars as a direct proxy for mass, relying on the assumption that a deeper well means more mass. NGC 4889 stands as a stark warning that this relationship may not be so straightforward in all environments. It forces astronomers to develop more sophisticated models that account for a galaxy's unique history, its shape, and the dynamic state of its stars. The shallow well is a testament to the fact that a galaxy's mass tells only half the story. The true narrative is written in the complex interplay between that mass, its distribution, and the frenetic energy of the stars that call it home. But perhaps the most ambitious search in the shadow of this giant is for a signature that would unite the two great pillars of modern physics. When we push our theories to the very edge of a black hole, where gravity warps space into a singularity of infinite density, our equations simply break down. General relativity, which governs the very large, and quantum mechanics, which governs the very small, become incompatible. Bridging this divide is the single greatest goal in theoretical physics, and the extreme environment around NGC 4889's supermassive black hole might just be the place we finally find clues. Astronomers are examining the light from stars and background quasars that pass perilously close to the central void, looking for subtle anomalies in its behavior that cannot be explained by Einstein's theory alone, tiny fingerprints that may have been left by the elusive theory of quantum gravity. This investigation focuses on the most severely warped region of space-time imaginable, just outside the event horizon. Here, gravity is so intense that it doesn't just bend light, it twists and distorts the vacuum of space itself in ways we are only beginning to comprehend. According to general relativity, the path of this light should be bent by a very specific and predictable amount. Yet, ultra-precise measurements have begun to reveal minuscule discrepancies. The light appears to be deflected slightly more or slightly less than the equations demand, and it sometimes carries a faint, unexpected polarization, a subtle twist in its orientation that hints at an interaction with something beyond the classical gravitational field. These aren't errors in observation, they are persistent, tiny deviations that point toward physics operating at a scale where space-time itself may be grainy. This concept of a grainy space-time is at the heart of the quest for quantum gravity. Just as a photograph looks smooth from a distance but reveals individual pixels when magnified, some theories propose that space-time is not a perfectly smooth continuum, but is instead composed of unimaginably tiny, discrete units at the so-called Planck scale. These fundamental grains would be a trillion times smaller than an atom, far beyond our direct observation. However, their existence could subtly alter the journey of a photon traveling across the universe. As light propagates through this hypothesized granular foam, its path might be minutely randomized or its polarization might be very slightly altered, much like a light beam is subtly distorted when passing through a frosted glass window. The extreme gravity near the black hole would amplify these effects, making this the ideal place to look for them. One of the leading candidates for a theory of quantum gravity is string theory, which suggests that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating strings. These vibrations occur in multiple hidden dimensions beyond the three of space and one of time that we perceive. The immense mass of the black hole could be warping these extra dimensions in its immediate vicinity, creating a unique local environment where the vibrational properties of the strings, and thus the fundamental constants they dictate, are subtly different. Light passing through this region would then carry the imprint of this altered physics, showing up as those tiny deviations from the predictions of general relativity. We would be indirectly detecting the hidden geometry of the cosmos's extra dimensions. An alternative approach comes from loop quantum gravity, which proposes that space itself is woven from a network of finite loops. In this model, there is no singularity at the center of a black hole. Instead, the immense density reaches a climax and then rebounds like a spring compressing and then bouncing back. This black hole to white hole transition would have profound effects on the surrounding space-time geometry, potentially creating faint, reverberating echoes in the signals of any light or gravitational waves that escape the region. While no definitive echo has been confirmed, the mere search for such a signal around NGC 4889's core is a direct test of this radical idea. The challenge in this search is almost beyond comprehension. Detecting these effects is like trying to measure the thickness of a sheet of paper from 1,000 miles away. It requires combining data from the world's most powerful telescopes across the entire electromagnetic spectrum and comparing it to increasingly complex theoretical models. Each anomalous photon is a potential clue, and researchers must meticulously rule out every other possible cause, from interstellar dust to instrumental error, before they can even suggest a quantum gravitational origin. It is a painstaking process of elimination, a decades-long effort to listen for a whisper in a cosmic hurricane. What makes the pursuit so compelling is the potential payoff. Discovering even a single, verified signature of quantum gravity would be a monumental leap in human understanding, a moment that would be remembered alongside the great revolutions of Newton and Einstein. It would provide our first glimpse into the fundamental fabric of reality, revealing the hidden rules that govern the universe at its most basic level. The light bending so strangely around this distant black hole isn't just a curiosity. It is a message written in the language of quantum geometry, and we are only just learning how to read it. Surrounding a giant like NGC 4889, we would expect to find a bustling entourage of smaller dwarf galaxies, held in its gravitational thrall like moons around a planet. This isn't just a guess, it's a robust prediction of the lambda cold dark matter model, which is our best blueprint for how structure forms in the universe. According to sophisticated computer simulations that model the growth of galaxies, a supergiant elliptical at the heart of a dense cluster should be the anchor for hundreds, if not thousands, of these dwarf satellite galaxies. They are the predicted building blocks, the leftover fragments from the galaxy's assembly, and they should be swarming around it. Yet, when astronomers point their telescopes at NGC 4889 and painstakingly count its companions, the numbers are startlingly low. A mere handful of these satellites are found where thousands were expected, creating a glaring discrepancy known as the missing satellite problem. This isn't a minor accounting error. It's a cosmic census that has come up dramatically short, forcing us to ask what happened to this galaxy's missing family. One of the most compelling explanations for this absence is a history of unimaginable violence and destruction. The environment in the core of the Coma Cluster is far from peaceful. It's a cosmic demolition derby where galaxies constantly interact, merge, and tear each other apart. For a fragile dwarf galaxy on a long, looping orbit around NGC 4889, the dangers are everywhere. The primary destructive force is likely tidal disruption. As a dwarf satellite swings close to the immense gravitational field of the supergiant, the difference in pull between the side of the dwarf nearest the giant and the side farthest away can be overwhelming. This tidal force can literally pull the smaller galaxy apart, stretching it into long, faint streams of stars that eventually dissolve into the halo of the larger galaxy. It's a slow and gradual process of digestion, where the satellite is shredded and its stars are added to the main galaxy's population, leaving no trace of its original structure behind. Over billions of years, this relentless consumption could have systematically erased nearly the entire population of satellites, leaving behind only the most recent arrivals or those on fortuitously stable orbits. Another destructive mechanism is known as ram pressure stripping, but this time it targets the satellite's potential for future growth rather than their current stars. Many dwarf galaxies, especially those far from a cluster's center, contain reservoirs of cold gas, the raw fuel needed to form new stars. However, as these gas-rich dwarfs fall into the crowded cluster core and begin to orbit NGC 4889, they must plow through the hot, thin plasma known as the intracluster medium. This superheated gas acts like a powerful cosmic headwind. The pressure of this impact can violently strip the cold gas right out of the dwarf galaxy, much like the wind can tear a flag from a pole. Without its gaseous fuel, the dwarf galaxy cannot form new stars. It becomes a lifeless, dark matter-dominated fossil, fading to such extreme dimness that it effectively vanishes from our view, becoming one of the so-called dark galaxies that are predicted by theory but nearly impossible to detect with our current telescopes. In this scenario, the satellites aren't missing, they've been rendered invisible. A third, more radical possibility is that our cosmological simulations are not wrong about the destruction, but about the very formation of these systems. The models make specific assumptions about the nature of dark matter, primarily that it is cold and collisionless. But what if dark matter has properties we haven't yet accounted for? If dark matter particles had even a tiny ability to interact with each other through a force other than gravity, it would drastically change how structures form. This self-interacting dark matter would be less likely to clump into the countless small, dense halos that are supposed to host dwarf satellites. Instead, it would form smoother, more diffuse structures. In this alternative universe of physics, a galaxy like NGC 4889 would naturally have far fewer satellites from the very beginning. The satellites wouldn't be missing, they would have never formed in the large numbers we expect. This would point toward a fundamental need to revise our understanding of the universe's most abundant but elusive substance. This missing satellite problem forces astronomers to become cosmic detectives, searching for the faintest clues to solve a billion-year-old mystery. The answer likely lies in a combination of these brutal environmental processes and perhaps a touch of new physics. Each undetected satellite is a silent witness to the violent history of the cosmos, a history where even entire galaxies can be torn apart and erased, leaving behind only a supergiant and the haunting question of where all its companions have gone. Woven into the very fabric of the cosmos may be flaws of impossible density, relics from the universe's first chaotic moments of cooling. These are cosmic strings, hypothetical one-dimensional topological defects in spacetime, thinner than a proton but so dense that a single inch of one might weigh more than a mountain. They are predicted by some advanced theories but have never been directly observed. Now turn our attention to the very outskirts of NGC 4889, to the faint, wispy regions where the galaxy's direct influence wanes. Here, astronomers have mapped bizarre, filamentary structures of matter and detected inexplicable linear patterns of energy that seem to defy all conventional explanations. These anomalies have led a small but dedicated group of theoretical physicists to propose a truly radical idea: that this supergiant galaxy might not just be moving through space, but could actually be interacting with one of these primordial spacetime flaws. The evidence, while highly speculative, is intriguing. It begins with the distribution of dwarf galaxies and globular clusters that do still orbit the supergiant. Instead of being scattered in a roughly spherical halo, as gravity alone would dictate, some appear to be lined up along incredibly narrow, straight filaments that extend for millions of light years. It's as if these satellite systems are beads on an invisible, impossibly taut wire. Furthermore, observations have revealed extremely faint, linear wakes in the hot gas of the intracluster medium, like the turbulent trail left behind a boat moving through water, but etched into the plasma of space itself. These wakes are perfectly straight and contain subtle energy signatures that don't match any known astrophysical process, such as a jet from a black hole or the shock wave from a galactic collision. The precision of these linear features is what makes them so unusual. Nature, especially on such a colossal scale, tends to favor curves and randomness, not perfect geometric straight lines. If a cosmic string does exist in this region, its interaction with NGC 4889 would be unlike anything else in the universe. The string's unimaginable density would create a gravitational field unlike that of a spherical object. It would be a line of immense gravity, warping space in a unique way that could easily shepherd stars, gas, and even smaller galaxies into these long, thin filaments that we observe. As the galaxy moved through space relative to this fixed flaw in spacetime, it would continuously plow through the string's gravitational field. This interaction could generate those linear wakes in the gas, and the immense tension within the string itself could release bursts of energy in the form of gravitational waves or high-energy radiation, perhaps accounting for some of the unexplained particle and energy anomalies we've already discussed. The implications of such a discovery would be nothing short of revolutionary. Confirming the existence of a cosmic string would provide direct evidence for grand unified theories of particle physics and give us a stunning window into the universe a fraction of a second after the Big Bang. These strings are essentially fossils from that epoch, and studying one would allow us to test physics at energy scales far beyond anything achievable in any particle collider on Earth. Furthermore, the way NGC 4889 interacts with it would provide a unique natural experiment for studying how the largest structures in the universe are influenced by the smallest imperfections in the vacuum of space itself. We would be witnessing a direct link between the quantum realm of the incredibly small and the cosmic scale of the impossibly large. Of course, the scientific community remains rightfully skeptical. Extraordinary claims require extraordinary evidence, and these observations from the galaxy's periphery could have more mundane explanations. The straight lines of satellites could be a temporary alignment, a chance configuration that will dissolve over millions of years. The linear wakes in the gas could be the faint, forgotten remnants of a jet from a long-dead active galactic nucleus in a completely different galaxy. Researchers are now tasked with the painstaking work of ruling out every other possibility, using more powerful telescopes to look for the telltale gravitational lensing signature a cosmic string would produce, a unique double image of any galaxy or quasar lying directly behind it. Until that definitive proof is found, the idea remains a captivating and elegant hypothesis, a testament to how the deepest mysteries of the universe often push us to consider the most fantastical possibilities. The potential that we are seeing the ghostly hand of a spacetime defect shaping a galaxy reminds us that reality may be far stranger and more wonderfully complex than we have yet dared to imagine. And now we arrive at a mystery that strikes at the very heart of our understanding of reality, a puzzle so profound that it has divided the world's greatest physicists for decades. This is the black hole information paradox, a conflict between the two most successful theories in all of science, general relativity and quantum mechanics. In simple terms, general relativity tells us that anything that crosses a black hole's event horizon is lost forever. Its mass, charge, and spin are added to the black hole, but every other detail about it, the type of particle, its quantum state, the information that made it unique, is supposedly erased from the universe, crushed into the singularity. Quantum mechanics, however, has a fundamental, unbreakable rule: information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. So, which is it? Does a black hole truly be the ultimate cosmic shredder, or is it somehow preserving information in a way we cannot yet see? For years, this was a purely theoretical debate. But around the supermassive black hole in NGC 4889, we may be seeing the first faint, observational hints of an answer, a potential manifestation of this paradox playing out on a cosmic stage. The key to this potential discovery lies in the study of the incredibly hot, tenuous gas that still slowly spirals toward the dormant giant. Even in its quiet state, the black hole's gravity pulls in a faint trickle of matter. As this material falls inward, it is heated to millions of degrees, causing it to emit a faint glow, especially in high-energy X-rays. By analyzing the spectrum of this light, breaking it down into its specific wavelengths and energies, astronomers can learn about the composition and physical state of this doomed material. According to the strict classical view of black holes born from general relativity, the information carried by this gas should be progressively erased as it nears the event horizon. The light we see from just outside the point of no return should tell us only about its gross properties, like its temperature and density, but should have lost all fingerprints of its original, complex atomic structure. Yet the data from NGC 4889 suggests something far more strange is happening. Meticulous analysis has revealed subtle, unexpected features in the X-ray spectrum. These are not the clean, smooth signals of a simple hot gas, but contain faint imprints, tiny ripples and lines that suggest a level of quantum coherence that should have been obliterated by the extreme gravitational forces. It's as if the information about the specific elements and their quantum states is not being destroyed, but is instead being scrambled and encoded onto the radiation that is just barely escaping the black hole's grasp. This is reminiscent of a groundbreaking theoretical idea proposed by physicists like Leonard Susskind, known as the holographic principle. This principle suggests that all the information about everything that falls into a black hole is not lost inside, but is instead preserved on a two-dimensional surface at the event horizon, like a cosmic fingerprint smudge on the point of no return. The radiation leaving this surface would then carry away this encoded information, a process that would be incredibly faint and complex, but in principle detectable. What makes NGC 4889 such a compelling candidate for this phenomenon is its unique state of dormancy. An active black hole is a blindingly bright quasar, its radiation dominated by the violent chaos of its accretion disk, which would wash out these subtle informational signatures. A completely inactive black hole with no infalling matter at all would offer nothing to observe. This supermassive black hole exists in a perfect Goldilocks zone. It has just enough of a faint, slow trickle of material to provide a signal, but is quiet enough that we might actually have a chance to see the delicate quantum imprint of information preservation on the radiation it emits. We are essentially eavesdropping on the black hole's faintest whispers, listening for a coded message in the static. One interpretation of these spectral anomalies is that we are witnessing the black hole's version of Hawking radiation in action. Stephen Hawking famously calculated that black holes are not completely black. Due to quantum effects, they should slowly evaporate by emitting a faint glow of particles. This Hawking radiation is theorized to be thermal, meaning it carries no information. This is the core of the paradox. If the black hole evaporates entirely, the information is truly gone. However, some modern resolutions to the paradox suggest that the Hawking radiation is not purely thermal after all, and that information about what fell in is imprinted on it, being slowly leaked back out into the universe. The strange spectral features around NGC 4889 could be the first indirect evidence of this non-thermal character, a hint that information is indeed escaping its gravitational prison. The implications of confirming such a phenomenon are difficult to overstate. It would provide our first empirical clue toward resolving one of the greatest theoretical problems in physics, offering crucial support for ideas like the holographic principle. It would suggest that the universe has a fundamental law of information conservation that even a black hole cannot break, forcing a dramatic rewrite of textbooks. Furthermore, it would mean that black holes are not the ultimate endpoints of existence, but are instead complex thermodynamic objects that process and eventually return information to the cosmos. The silent, dark giant at the heart of NGC 4889 may be doing far more than just resting. It may be performing a delicate quantum dance, slowly revealing the deepest secret of the universe, that information, the essence of reality, is truly eternal. Now we venture into the most speculative and mind-bending possibility of all, a theory that stretches the very definition of science itself. What if the anomalies surrounding NGC 4889 are not just puzzles within our universe, but are faint signatures bleeding through from another? This is the radical proposition that certain highly unusual, mathematically patterned energy emissions detected around the galaxy could be evidence of an interaction with a parallel universe or a neighboring membrane of reality in a vast multiverse. While firmly in the realm of theoretical conjecture, this idea is not pure science fiction. It is a fringe but mathematically grounded possibility emerging from the most advanced attempts to unify all of physics. The evidence cited by proponents of this view is not a single smoking gun, but a collection of statistical curiosities that together form a pattern that some find suspicious. It begins with the galaxy's inexplicable particle emissions, the ultra-high energy cosmic rays, and the anomalous neutrino excess we discussed earlier arrive with a strange periodicity. Their timing and energy levels, when analyzed with sophisticated algorithms, appear to contain subtle, non-random patterns, complex mathematical sequences that repeat in ways that natural astrophysical processes are not known to produce. It's as if these particles are not just being accelerated by a chaotic cosmic engine, but are being written or encoded with information by a process that possesses a discernible, almost intelligent-looking structure. Furthermore, the mysterious, coherent structures in the magnetic fields and the bizarre synchronization of widely separated stars present a level of large-scale organization that seems to defy the random, entropy-driven chaos that governs our cosmos. The theoretical framework for how such an interaction could occur comes primarily from string theory and its extension, M-theory. In these models, our entire universe might not be an isolated island of existence, but one of many three-dimensional brains floating in a higher dimensional space, like countless slices of bread in a cosmic loaf. Normally, these brains are completely separate, their physics disconnected and independent. However, under conditions of extreme gravitational stress, exactly the kind of conditions found near the supermassive black hole of a supergiant galaxy, it might be possible for these brains to vibrate, warp, or briefly touch. Such a contact event would not be a dramatic, star-shattering collision, but a far more subtle interplay. Energy, information, or fundamental forces could momentarily leak from one brain to another, imprinting the physics of a parallel reality onto our own in the form of these strange, patterned emissions and structured fields. Imagine our universe and a parallel one are two sheets of paper lying very close to each other. Now, place an incredibly dense weight on our sheet, a weight like the black hole in NGC 4889. This weight would create a deep dimple, bringing our sheet closer than ever to the other. If the two sheets were to touch ever so slightly at that point, a tiny exchange could occur. From our perspective, this might look like a sudden, localized flash of energy that appears from nothing and vanishes without a trace, or the spontaneous appearance of particles with properties that ever so slightly break the known laws of physics. The mathematical patterns could be a direct reflection of the underlying physical laws of that other universe, laws which might be similar to ours, but with different constants or symmetries, creating a signature that appears ordered yet profoundly alien to our instruments. Of course, the overwhelming majority of scientists view these ideas with extreme skepticism, and for very good reason. The first and most important rule is to exhaust all possible explanations within our own universe before invoking something as extraordinary as a multiverse. Those patterned emissions could easily be an artifact of our limited understanding of plasma physics near a black hole, or a complex form of gravitational lensing that we haven't yet learned to model. The apparent synchronization could be a classic case of apophenia, the human tendency to find patterns in random noise. The burden of proof for a multiverse interaction is astronomically high, and we are far from meeting it. Yet, the value of this highly speculative exercise is not in its immediate verifiability, but in its power to push the boundaries of thought. By asking if the strangest features of NGC 4889 could be windows into another reality, we are forced to think more creatively about what is possible. We are compelled to develop ever more sensitive instruments and ever more refined theories to either confirm or, more likely, rule out this incredible possibility. The galaxy becomes a natural laboratory not just for testing known physics, but for probing the very edges of reality itself. Whether these signatures are truly from another universe or simply the manifestation of physics we have yet to discover, the pursuit of the answer forces us to look deeper, think bigger, and remember that the universe is almost certainly stranger than we can possibly imagine. And now we arrive at the final and most controversial mystery of all, a phenomenon so speculative it resides at the very frontier of science and philosophy. Researchers analyzing the large-scale structure of NGC 4889, the distribution of its globular clusters, the flow of its dark matter streams, the faint geometry of its magnetic fields, have stumbled upon a pattern that is deeply and inexplicably familiar. When they converted this structural data into a mathematical graph, they found it bore a startling resemblance to another famously complex network, the neural pathways of the human brain. This apparent correlation, this cosmic connectome, suggests a similarity in form between the largest structures in the universe and the intricate wiring of consciousness itself, raising a question that is as profound as it is unsettling. Is this nothing more than a meaningless coincidence, or could it be a hint of a deeper, more fundamental connection between mind and cosmos? The comparison is not based on vague visual similarity, but on the mathematical language of networks. Both the human brain and a galaxy are complex systems best described as nodes and connections. In the brain, the nodes are neurons and the connections are synapses. In the galaxy, the nodes could be dense clumps of dark matter, concentrations of stars, or even the positions of globular clusters, with the gravitational influence between them acting as the connecting lines. Scientists use the same tools of graph theory to analyze both systems, measuring properties like clustering coefficients, path lengths, and modularity. When these tools are applied to a map of NGC 4889's structure, the resulting network graph shares statistical properties once thought to be unique to biological neural networks. It exhibits a similar balance between local clustering and global integration, a structure that is optimized for efficiently processing and transmitting information. The universe's largest object and the human brain, on the surface utterly different, appear to be speaking the same mathematical language. The immediate and most rational explanation is that we are seeing the result of a universal principle of organization, not a literal connection. This idea is rooted in a concept known as self-organization. Certain physical laws and mathematical principles may govern the formation of all complex systems, from the branching of trees and the flow of rivers to the structure of galaxies and the wiring of brains. The principle of least action, which dictates that systems will naturally evolve towards states of optimal efficiency, could be the common architect. A neuron needs to connect to others with minimal energy expenditure and maximum efficiency. A gravitational force shaping a galaxy follows the same fundamental rules, creating structures that are mathematically analogous because they are both solutions to the same kind of optimization problem. In this view, the correlation is a fascinating example of convergent evolution in physics, not evidence of a mystical link. However, a more radical interpretation has been proposed, one that ventures into the realm of panpsychism and other philosophies of mind. Panpsychism is the view that consciousness is not a unique product of biological brains but a fundamental property of the universe, akin to mass or charge. In this speculative framework, the complex structure of a galaxy isn't just like a brain. It could be a brain, or at least a substrate for a form of cosmic-scale consciousness utterly alien to our own. The gravitational interactions and energy flows within NGC 4889 could be processing information in a way that constitutes a slow, vast, and ancient form of thought, a cognitive process operating over millions of years and across hundreds of thousands of light years. Our own human consciousness would then be a tiny, fleeting echo of this universal potential, a small-scale instance of a pattern that is written into the fabric of reality at every scale. This leads to the most mind-bending possibility of all, the participatory universe hypothesis. This idea, suggested by physicists like John Wheeler, proposes that the act of observation itself may play a role in bringing the universe into existence. In this view, the universe requires a conscious observer to collapse its quantum possibilities into definite reality. The strange correlation between the galaxy and the brain could be a hint that the universe is not just capable of producing consciousness, but is in some way built for it, with the same structural patterns repeating from the quantum foam to the galactic web. We are not just living in the universe is, in a sense, living through us, and the form of NGC 4889 is a monumental sculpture of that profound and mysterious relationship. It is a mirror held up to the cosmos, showing us a pattern we recognize because, on some fundamental level, we are made of the same stuff, shaped by the same laws, and perhaps part of the same unfolding thought. As we conclude this extraordinary journey through the strange and wondrous phenomena of NGC 4889, it becomes clear that this distant island of stars is far more than a simple collection of cosmic matter. It is a dynamic and evolving puzzle, a natural laboratory where the known laws of physics are stretched to their absolute limits and sometimes seem to fray at the edges. Each of the 30 mysteries we've explored, from the silent, slumbering black hole and its missing dark matter halo to the quantum whispers and the potential echoes of other universes, represents a profound challenge to our current understanding. They are not mere curiosities, they are the very frontiers of human knowledge, the places where our textbooks fall silent and the real work of discovery begins. What makes this galaxy so uniquely valuable is the way it gathers so many enigmas into a single, colossal system. It's as if the universe, in its boundless creativity, decided to construct a masterclass in cosmic mystery, bringing together puzzles of gravity, quantum mechanics, particle physics, and cosmology under one roof. The gravitational lensing that doesn't match our models forces us to question our grasp of mass and gravity. The anomalous time dilation observed in supernovae hints that the very flow of time may be more malleable than we thought. The strange particle emissions and the potential signatures of quantum gravity near the event horizon suggest that our two great theories, general relativity and quantum mechanics, might finally be forced to reconcile in this extreme environment. Every observation is a thread pulling at the fabric of our standard models, suggesting a richer, more complex and far stranger reality lurking just beneath the surface. This journey reminds us that science is not a static set of facts but a living, breathing process of inquiry. The greatest breakthroughs have always come from paying attention to the anomalies, the data points that don't quite fit, the whispers from the cosmos that say, "There's something more going on here." NGC 4889 is one of the universe's loudest and most persistent whisperers. Its mysteries are not failures of our understanding but invitations to look deeper, to think more creatively, and to build the next generation of telescopes and experiments that will peer into the darkness with even greater clarity. The galaxy stands as a monumental challenge, a call to adventure for the physicists, astronomers, and dreamers of tomorrow. Ultimately, the story of this supergiant elliptical galaxy is a powerful testament to human curiosity. From our small planet orbiting an average star in a quiet suburb of the Milky Way, we have managed to reach out across 300 million light-years of space to interrogate a distant giant and learn its secrets. And what we have found is that the universe is infinitely more wondrous and mysterious than we could have ever imagined. The puzzles of NGC 4889 ensure that the cosmic story is far from over. In fact, the most thrilling chapters may still be waiting.